Pepsi, Dr. Pepper, and Redbull are built from formulas the world can taste but never fully understand. Inside high-speed bottling plants, dark syrups and sharp carbonation meet exact recipes that define drinks unlike anything before it. Today, we step inside the production lines behind these legendary beverages and uncover how 3 secretive formulas become billions of instantly recognizable products. A PET preform enters the Pepsi line as a short, thick tube of transparent plastic. Its bottleneck is already finished. The threads, sealing surface, and tamper ring support are molded into place before the body is expanded. The lower section is still compact and heavy, holding enough plastic to form a full bottle. The preforms drop into a feeder, where mechanical tracks orient them neck up. They travel into a heating oven in single file. Infrared lamps warm the body of each preform, while rotating holders spin it continuously. Rotation spreads heat evenly around the plastic wall. The neck remains cooler because its dimensions must not change. When the plastic reaches the correct softness, transfer arms lift each preform into a blow molding station. A steel mold closes around it. Inside the mold is the final Pepsi bottle shape, including the shoulders, label panel, grip features, and pressure-resistant base. A stretch rod drives downward through the heated preform. It pulls the softened plastic lengthwise. Almost immediately, compressed air fires into the interior. The plastic balloons outward until it touches every chilled surface of the mold. The small tube becomes a full bottle in a fraction of a second. The mold opens. A clear, lightweight bottle leaves the station by its neck ring. It is still warm, but already rigid enough for conveying. The bottle moves through overhead air conveyors, suspended below rails, while streams of air push it forward. Before filling, the empty bottles enter a rinser. Each bottle is gripped by the neck, flipped upside down, and exposed to filtered rinsing air or treated water. Any loose particle is removed from the inside surface. The bottle drains briefly, turns upright again, and enters the filling section. While the packaging line forms and cleans the bottles, the beverage is assembled inside closed stainless steel equipment. Water enters the plant treatment system first. It passes through particle filters that remove suspended solids. Activated carbon stages remove unwanted tastes and odors. Additional filtration and conditioning equipment brings the water to a stable mineral and clarity specification. The treated water collects in sealed storage tanks. Level sensors monitor the volume. Temperature probes track the condition of the water. Pumps send part of it towards syrup production and keep another controlled stream available for final beverage blending. Pepsi syrup begins in a mixing tank with a measured charge of treated water. The tank agitator starts turning, creating a deep circular flow. Sweetener is introduced into this moving liquid. Depending on the production formula, the sweetener may be dry sugar, liquid sugar, or a liquid sweetening system. When granulated sugar is used, the crystals disappear into the rotating water. The liquid gradually becomes denser and more reflective. Mild heat can assist dissolution, allowing the sweetener to blend fully without leaving gritty material behind. The sweetened liquid leaves the dissolving tank through a filtration stage. Fine filters catch undissolved particles before the syrup reaches later machines. The filtered stream moves into a finished syrup vessel. Pepsi concentrate is metered into this tank through enclosed pipework. It enters as a dark, highly concentrated stream. Pumps and flow meters control the quantity precisely. As the agitator turns, the concentrate folds through the sweet base, rapidly changing its color and aroma. The concentrate supplies the specific cola flavor system and caramel-toned appearance required for Pepsi. Acidity ingredients are incorporated according to the formula. Each addition is measured before it enters the tank, and mixing continues until the syrup reaches a uniform condition throughout the vessel. The finished syrup is too concentrated to fill directly. It flows to a proportioning unit, where it will meet a much larger stream of treated water. The proportioner receives syrup through one controlled line and water through another. Flow meters measure both streams continuously. Automatic valves adjust their movement so the mixing ratio does not drift. The system corrects itself immediately when flow or pressure changes. Inside the blending chamber, dark syrup spreads into the water. The beverage reaches its final sweetness, flavor concentration, acidity, and color, but it still lacks carbonation. At this moment, it is flat Pepsi. The blended liquid enters a chilling system. It passes through thin channels inside a heat exchanger while a cold cooling medium flows nearby on the opposite side of metal plates. Heat leaves the drink quickly. The temperature drops without exposing the beverage to outside air. Chilling prepares the liquid for carbon dioxide. Cold Pepsi can absorb gas more efficiently and can be filled with less foaming. The beverage may also move through a deaeration unit, where reduced pressure draws unwanted dissolved air from the liquid. Small bubbles rise out of the stream before it continues. Carbon dioxide enters through pressure regulators and filtered gas lines. In the carbonator, the chilled beverage is held under controlled pressure while carbon dioxide dissolves into it. The liquid becomes lively and sparkling without forming uncontrolled foam inside the system. From this point onward, the beverage must remain under pressure. Closed pipes carry carbonated Pepsi directly toward the filler bowl. The rotary filling machine is surrounded by continuously moving empty bottles arriving from the rinser. A star wheel separates the bottles into exact intervals and guides each one under a filling valve. The bottle lifts into sealing contact with the valve. Gas pressure inside the bottle is balanced with the pressure in the filler before liquid enters. This prevents the carbonated drink from surging or erupting into foam. The valve opens. Cold Pepsi flows smoothly down the inside wall of the bottle. The liquid level rises in a controlled column, dark and glossy, beneath the overhead machine lights. When the exact fill point is reached, the valve closes. Each filled bottle moves away from the filler and immediately toward the capper. There is little open travel between these stages because the carbonation must be captured quickly. Plastic caps arrive in bulk and enter a sorting unit. The feeder turns every cap into the same orientation and sends them down a chute. Rotating capping heads collect the caps one by one. A filled bottle passes underneath. The capping head lowers, places the cap over the threaded neck, and turns it with a measured torque. The liner presses against the sealing surface. The tamper band locks below the bottle ring. The beverage is now sealed inside a pressure-tight container. Other Pepsi package lines use different sealing equipment. Empty aluminum cans pass through air rinses before filling, then receive metal lids. In the seamer, each lid and can edge are folded together by rotating rolls. The double seam traps the carbonation inside the can. Glass bottles can receive metal crown caps pressed and crimped around the bottle mouth. After sealing, the bottles travel through inspection systems. Sensors check the liquid level through the bottle wall. Cameras verify that every cap is present, straight, and fully seated. Other detectors examine bottle shape, cap position, and possible leakage. A bottle outside tolerance is removed from the conveyor by a rapid pusher or directed air burst. The correctly filled stream continues without pausing. The bottles now enter the labeling area. Printed plastic label film unwinds from a large roll. Registration sensors read tiny marks in the printed pattern, so each label is cut at exactly the correct point. The labeler cuts individual pieces of film and transfers them towards spinning bottles. A small amount of adhesive fixes the leading edge to the bottle surface. As the bottle rotates, the label wraps around its body. A second adhesive point secures the trailing edge. Rollers and brushes smooth the film against the bottle panel. The label sits tightly around the container, displaying its blue, red, and white print while leaving the cap and liquid visible above and below it. Some package formats use pressure-sensitive labels instead. These are peeled from a backing liner and pressed onto the container by soft rollers. For cans, the printed design is normally already applied to the metal body before beverage filling. Every finished container receives production coating. An inkjet head sprays tiny droplets onto the cap, bottle shoulder, label area, or can base as the package moves past. The coat is applied in milliseconds, leaving a readable batch and time mark. Because the beverage has been chilled, moisture may gather on the outside of the package. The containers pass through an air knife station. Narrow blades of fast-moving airstrip droplets from the cap, bottle shoulder, label seam, and base. The surface becomes dry before secondary packaging begins. Guide rails then divide the bottle flow into several lanes. Timing screws adjust the spacing. Collating equipment gathers bottles into predetermined pack patterns. A continuous stream of single bottles becomes groups arranged in rows. For shrink-wrapped formats, a film sheet surrounds each group. The pack enters a heat tunnel. Hot air causes the film to contract around the bottles, tightening against the shoulders and lower walls. The individual containers become one handled unit. A dark stream of Dr. Pepper concentrate enters a moving tank of sweet syrup and disappears beneath the turning surface. The tank is sealed stainless steel with an agitator rotating from below. Inside, the syrup is already dense and smooth. It has been prepared from treated water and a measured sweetener system, blended until no dry crystals or heavy streaks remain. When the concentrate enters, the liquid changes quickly. Its color deepens to a rich brown, and the entire batch takes on the concentrated flavor base that will later become finished Dr. Pepper. The concentrate is not the final drink. It is a powerful flavor system measured in small quantities against a much larger volume of water and sweetener. Metering pumps deliver it through closed piping. Flow meters or weighed vessels confirm the addition. The agitator keeps pulling liquid inward, folding the concentrate through the syrup until the mixture reaches the same strength and color from top to bottom. Before this stage, water has already moved through its own preparation system. Incoming water passes through particle filters that remove suspended material. Activated carbon beds reduce unwanted tastes and odors. Additional polishing equipment brings the water to a stable mineral condition and clarity. The finished water collects in enclosed storage tanks, ready for syrup production and final dilution. Sweet syrup forms in a separate tank. A programmed amount of treated water enters first. Sugar or another specified sweetener is added, while large mixer blades rotate. Dry crystals, when used, sink into the moving liquid and dissolve as heat and agitation work through the batch. The mixture becomes thicker, clearer, and more reflective than plain water. The syrup then passes through fine filtration. Any undissolved material is removed before it can reach valves, pumps, or filling heads. From there, the filtered sweet base receives the Dr. Pepper concentrate and required formula additions. The finished syrup is intense, heavy, and still. It contains the beverage character, but it is far too concentrated and has no carbonation. The syrup leaves its holding tank through sanitary pipework and reaches a proportioning unit. Another pipe brings treated water from storage. The two streams remain separate until their flow rates are measured. The proportioner checks them continuously, opening and closing automatic valves in tiny movements to maintain the required blend ratio. Inside the blending chamber, the concentrated syrup is diluted. The thick, dark liquid thins immediately as it merges with water. Its viscosity drops, but its color remains deep. The mixture now has the sweetness, acidity, and flavor strength of Dr. Pepper, although it is still flat and warm compared with the finished drink. The flat beverage moves into a chilling section. It passes through narrow passages in a plate heat exchanger. On the opposite side of each thin metal plate, chilled fluid draws heat away. The drink temperature falls rapidly without exposing the liquid to open air. Cooling matters because carbon dioxide dissolves more readily into a cold beverage. A chilled drink also behaves more cleanly inside the filler, with less foam breaking out when it enters the package. The colder stream continues toward the gas handling equipment. Before carbonation, dissolved air may be removed from the water or blended beverage. In a deaeration vessel, reduced pressure encourages trapped gases to escape. Tiny bubbles rise out of the liquid as it flows through the chamber. The treated stream leaves with less unwanted gas competing with the carbon dioxide that will be added next. Carbon dioxide arrives through regulated stainless steel lines. Pressure control equipment stabilizes the gas before it enters the carbonator. Inside that enclosed machine, cold Dr. Pepper and carbon dioxide meet under pressure. The gas dissolves into the liquid, building the sharp, sparkling texture of the finished beverage. The carbonated drink stays inside pressurized piping from this point forward. It cannot be allowed to lose gas before sealing. Pumps and valves carry it toward the filler, while container lines approach from different directions. On a can line, empty aluminum cans begin as open cylinders arriving in closely packed rows. Guide rails narrow the flow into controlled lanes. The cans enter a twist rinser where curved tracks turn each container upside down. Filtered air or rinsing fluid blasts the interior. The cans drain, rotate upright, and move directly toward filling. A bottle line starts differently. PET preforms arrive as small plastic tubes with fully molded neck threads. Feeders orient the preforms and place them onto carriers. They enter an infrared oven, rotating as heating lamps soften the body evenly while leaving the neck stable. The hot preforms transfer into bottle molds. Each mold closes with the exact shape of the final container formed into its inner surface. A stretch rod extends the soft plastic downward. Compressed air then expands it outward against the chilled mold wall. In an instant, the thick preform becomes a full-size bottle with shoulders, side panels, and a pressure-resistant base. Fresh bottles leave the mold held by their neck rings. Air conveyors move them toward rinsing. Each bottle is inverted, cleaned internally with filtered air or treated water, drained briefly, then returned upright. The bottles are now empty, clear, aligned, and ready to capture carbonated Dr. Pepper. The filler is a large rotating machine. A circular bowl holds pressurized beverage above many filling valves. Containers enter through a star wheel that spaces each one precisely. Every can or bottle is delivered under its own valve as the carousel continues turning. For bottles, the neck presses into sealing contact with the filling valve. For cans, the open top is positioned beneath the filling assembly. The container is prepared for the pressurized liquid, so gas does not erupt violently when the drink enters. Pressure equalization keeps the beverage calm. The valve opens. Dr. Pepper flows into the container in a controlled path, often directed along the inner wall to limit turbulence. In transparent bottles, the dark liquid rises smoothly from the base. A thin layer of bubbles appears near the top, then settles as the correct fill level is reached. The valve closes at the programmed point. Correct headspace remains above the liquid, allowing the sealed package to contain internal pressure properly. The filled container moves immediately out of the filler toward its closing machine. Cans receive lids first. A lid feeder separates thin aluminum ends and positions one over each filled can. The can then enters a seamer. Rotating tooling folds the lid curl and can flange together. One set of rolls forms the hook. Another compresses it into a tight double seam. The can leaves with the carbonated beverage trapped beneath a narrow metal seal. Peter bottles travel beneath rotating capping heads. Plastic caps arrive through a sorting feeder, all facing the same direction. A head picks up one cap, lowers it onto the bottleneck, and turns it to a controlled torque. The tamper band passes over the neck ring and locks into place as the closure tightens. Glass bottle formats use crown caps. A crown is positioned on the bottle mouth and pressed downward. The capper crimps its ridged skirt beneath the glass finish. The sealed glass bottle continues with the same pressurized drink enclosed inside. Sealed packages enter inspection immediately. Fill level sensors examine the amount of liquid. Cameras inspect cap position, crown placement, can lid presence, bottle shape, and package condition. Seam monitoring systems can evaluate can closure quality. Any package outside the programmed limits is removed from the line by a fast reject mechanism. Bottles then require labeling. A roll of printed label film unwinds beside the moving conveyor. Registration sensors read marks on the web, so each label is cut in the correct position. The cut label reaches a rotating bottle, receives small adhesive contact points, and wraps smoothly around the body. Rollers press the label against the bottle surface. The film tightens across the label panel without folds or loose edges. Glass packages may instead receive glued paper labels or pressure-sensitive labels applied by transfer pads and smoothing brushes. Cans usually arrive with their exterior design already printed, so they bypass wraparound labeling. Bottles and cans both pass the coding station. Inkjet heads fire tiny droplets onto a cap, bottle shoulder, label surface, or can base. Each package receives a compact production mark while remaining in motion. Because filling uses chilled liquid, condensation can form on the outside of the containers. The sealed packages move through air knives. Narrow, powerful sheets of air push droplets away from cap rims, shoulders, label seams, can lids, and bases. Dry packages travel more reliably through the equipment that gathers them into larger units. An empty aluminum can drops into a twisting rail and turns upside down before a single drop of Redbull enters it. The can is already formed, printed, and open at the top. Its walls are thin, lightweight, and shaped to withstand internal pressure once the carbonated drink is sealed inside. As the can moves through the rinser, filtered air blasts its interior. The can rotates upright again and joins a tightly spaced stream heading toward the filler. At the same time, the beverage is being assembled inside closed stainless steel tanks and pipework. The liquid begins with treated water. Incoming water passes through filtration equipment that removes fine suspended particles. Activated carbon treatment removes unwanted tastes and odors. Additional polishing stages stabilize clarity and mineral behavior. The treated water is collected in sealed holding tanks fitted with level probes, temperature sensors, and controlled outlet pumps. A portion of this water moves toward the syrup preparation area. Redbull is built differently from a dark cola. The finished liquid is pale and translucent, so the dissolved ingredients must create a clear, uniform beverage without visible sediment or cloudiness. A measured amount of treated water enters a blending vessel. The agitator begins turning beneath the surface. Sugar is introduced through a dosing system. When granulated sugar is used, the crystals fall into the moving water and begin dissolving immediately. The liquid grows heavier and more glossy as the sweetener concentration rises. Temperature control assists this stage. Warm liquid dissolves crystalline ingredients more efficiently, but the heat is regulated so later ingredients can be added under stable conditions. The vessel does not boil the mixture. It builds a clean, pumpable base that can carry the beverage components evenly. Once the sugar solution is smooth, it passes through filtration. Fine filters catch any remaining undissolved material before the liquid reaches precision dosing equipment. The filtered base returns to a blending tank or flows into an inline mixing system. Acidity components are added next. They enter as measured liquid or dissolved ingredient streams. The agitator folds them through the sweetened water. The base changes chemically. developing the sharp structure needed beneath the sweetness and carbonation. Energy drink ingredients are introduced in controlled quantities. Caffeine, taurine, vitamin ingredients, and flavor components are weighed or metered before entering the blend. Some arrive as prepared solutions, so they disperse quickly. Others are dissolved in a separate small tank before being pumped into the main stream. The dosing stage requires careful mixing because each ingredient must spread evenly through a large liquid volume. A concentrated addition entering one point in the tank cannot remain there. The agitator draws the stream downward, pushes it outward, and circulates it through the vessel until the blend has consistent concentration throughout. Flavor ingredients join through closed lines. They are added in small, precisely controlled amounts because they influence the final aroma and taste far more strongly than their volume suggests. The mixture remains light in color, unlike the deep syrup formed during cola production. The prepared beverage base is still stronger than the final drink if it has been assembled as a concentrate. It flows toward a proportioning unit, where another treated water stream meets it. Flow meters monitor both liquids. Automatic valves make continuous adjustments, so the formula remains steady as production runs at high speed. As the two streams combine, the beverage reaches its final dissolved ingredient concentration. It is now sweetened, acidified, flavored, and evenly blended, but it is not yet carbonated and is still too warm for controlled filling. The liquid passes through a heat exchanger. It flows along narrow metal channels, while chilled fluid travels through neighboring channels on the other side of thin plates. Heat leaves the beverage rapidly. The liquid remains enclosed while its temperature drops. Cold liquid absorbs carbon dioxide more effectively than warm liquid. Chilling also reduces foaming inside the filler. The canning line depends on this condition because a narrow aluminum can opening leaves little room for uncontrolled foam during high-speed filling. The chilled beverage may move through deaeration equipment before carbonation. Under reduced pressure, dissolved air is encouraged to leave the liquid. Small bubbles rise and separate from the stream. Removing excess air helps the carbonated beverage behave more predictably as it travels through the pressurized system. Carbon dioxide enters through regulated gas lines. Filters and pressure control equipment prepare the gas before it reaches the carbonator. Inside the enclosed carbonation unit, carbon dioxide contacts the chilled beverage under pressure. The gas dissolves into the liquid, producing the sparkling texture of finished Redbull. The beverage is now kept inside sealed, pressurized piping. It flows directly toward the filling machine, where the upright, internally cleaned cans are arriving in a synchronized stream. A rotary filler receives the cans through a star wheel. The star wheel separates them into exact positions and carries them beneath individual filling valves. The filler turns continuously, with each can following a curved path beneath the pressurized beverage bowl. The filling sequence begins as the can aligns with its valve. Pressure conditions are controlled so the carbonated liquid enters without excessive agitation. The valve opens and chilled Redbull flows downward into the aluminum container. The pale liquid rises quickly inside the can. The flow is designed to remain smooth, limiting foam and protecting the dissolved carbonation. When the correct volume is reached, the valve closes. A narrow space remains between the liquid and the top of the can, allowing the package to be sealed correctly under internal pressure. The filled can moves directly toward the lid station. Thin aluminum ends are stacked in a feeder and released one at a time. Each lid is positioned over a filled can before the open container can lose significant carbonation. The can then enters the seamer. This machine creates the pressure-tight closure without glue or heat sealing. The can body and lid rotate together while forming rolls press against their edges. The first seaming operation curls the lid edge around the can flange. The second operation compresses the folded metal tightly together. Multiple layers of aluminum interlock into a narrow double seam. The seam is compact, smooth, and strong enough to contain the carbonated drink. Sealed cans travel through immediate inspection. Sensors check the fill level without opening the package. Seam inspection systems examine the closure profile. Vision cameras look for dented cans, damaged tops, missing lids, tilted seams, or printed can defects. Any can outside the programmed tolerance is rejected from the moving line. A mechanical pusher or controlled air jet removes it, while accepted cans continue forward at constant speed. The cans then pass the coding station. A high-speed inkjet printer applies production information to the can base or another assigned surface. Tiny droplets form characters as the can moves beneath the print head. A vision reader can verify that the code is present and legible. Sprite is manufactured by preparing a citrus flavor syrup, blending it with treated water at a fixed ratio, carbonating the beverage to a precise dissolved CO2 level, then filling and sealing containers under counter. Pressure, so carbonation and aroma stay stable. Production starts with water because water chemistry controls acidity perception and carbonation behavior. Incoming water is filtered to remove suspended solids and then polished through fine filtration. Mineral content is adjusted to a target hardness and alkalinity, so the final drink has consistent bite. Water is then cooled because colder water holds CO2 more efficiently and reduces foaming during filling. A sweetener stream is prepared in parallel. For sugar-based production, granulated sugar is dissolved in heated tanks with agitation until the syrup is clear. Syrup concentration is measured by density and held in a narrow band because it determines final sweetness after dilution. The syrup is filtered to remove undissolved crystals that could seed crystallization or clog valves. For other sweetener systems, a concentrated solution is prepared and handled as a metered liquid feed with consistent density. The citrus flavor system is built as a concentrate that can be dosed precisely. Lemon and lime flavor components often include oil-based fractions that must be emulsified to remain stable in water. The flavor concentrate is mixed in a blending tank where carriers and emulsifiers are combined with flavor oils. High shear mixing reduces oil droplet size and stabilizes the emulsion. Droplet size control prevents separation and reduces ring formation at the surface of the final beverage. The concentrate is filtered to remove any particulate and to protect dosing pumps. Acid addition is managed as part of syrup formulation because pH defines freshness and also affects how sweetener is perceived. Acid is prepared as a liquid solution for accurate dosing. It is injected into the syrup or into the flavor concentrate depending on process layout. pH is measured and adjusted to a tight set point. Small changes in pH shift the balance between sharp citrus and sweetness. Buffer salts can be used in very small amounts to reduce drift, but the main control is acid dose. If the formulation includes a clouding system to support the citrus profile, it is prepared as an emulsion stream. Cloud systems are designed to keep a slight visual opalescence and to carry flavor. They are mixed under shear and then held with gentle agitation so they do not cream. Stability is verified by checking droplet size and separation rate. Once sweetener syrup, flavor concentrate, acid, and any cloud system are ready, they are combined into a finished syrup. The syrup is mixed with controlled agitation that avoids foaming. The syrup is then held at a stable temperature and delivered to the proportioning blender through metered pumps. Filters at this stage protect the blender and carbonator from particles and gel lumps. Final beverage blending is done with a proportioning system that meters syrup and chilled treated water. The ratio is controlled by mass flow meters or by volumetric meters with density compensation. Ratio accuracy is the main determinant of consistent taste. The blended stream is monitored by inline soluble solids measurement. When solids drift, the control system adjusts valve positions to correct the syrup-water ratio. Before carbonation, the blended beverage is commonly deaerated. Deaeration removes dissolved oxygen and entrained air. Oxygen dulls citrus aroma over time and increases oxidation in flavor components. Air also reduces carbonation efficiency because it occupies headspace in the carbonator and promotes foam. Deaeration is performed under vacuum, where the beverage spreads as a thin film. Vacuum pulls gases out and the liquid leaves with lower oxygen content. Carbonation follows, and it is controlled by temperature, pressure, and contact efficiency. CO2 supply is filtered and regulated to stable pressure. The cold beverage enters a carbonator, where CO2 is injected and dissolved under pressure. Many carbonators use a sintered stone or injector that forms fine bubbles. Fine bubbles create high surface area and dissolve quickly. The carbonator maintains a pressure high enough to keep CO2 in solution and prevent breakout. Dissolved CO2 level is monitored continuously. Instruments measure or infer carbonation based on temperature and pressure. The line targets a defined carbonation level that gives a crisp bite. If temperature rises, CO2 solubility drops and gas begins to break out. The system compensates by increasing pressure or improving cooling. Tight temperature control in the blending and carbonator sections therefore supports stable carbonation. Once carbonated, the beverage must be handled with low turbulence. High shear pumps and sharp piping bends can release CO2 and create foam. The line uses low shear pumps and smooth piping layouts. The product is kept under pressure all the way to the filler bowl. Pressure maintenance prevents CO2 loss and reduces foaming at the fill valve. Container handling runs in parallel with beverage. Preparation. Cans or bottles are conveyed, oriented, and cleaned. Cans are often rinsed and drained before filling. Bottles are oriented and may be rinsed or air-blown to remove dust. Plastic bottles may be supplied from blow molding and then transferred to the filler quickly. Container temperature can influence fill behavior because warm containers promote foaming. Lines manage container staging to avoid excessive warming. Filling is performed on counter-pressure fillers. The container is first sealed to the fill valve and pressurized with CO2 to match filler bowl pressure. This equalization reduces foaming when liquid enters. The fill valve opens and beverage flows in at a controlled rate. Fill level is controlled by a probe or by timed flow depending on equipment design. Controlled flow reduces turbulence and helps maintain carbonation. After the container reaches fill level, the valve closes and pressure is released in a controlled way. Controlled release prevents the liquid from erupting and prevents excessive foam that could contaminate the seal. For cans, the lid is applied and the can is seamed immediately. For bottles, the cap is applied immediately with controlled torque. Rapid sealing locks carbonation and reduces oxygen pickup. Headspace control is part of maintaining carbonation and flavor. The fill is set to leave a defined headspace volume. Many lines apply a CO2 jet just before capping or seaming. This displaces air from the headspace and reduces oxygen content. Reduced oxygen protects citrus aroma and reduces flavor drift. Headspace CO2 also supports equilibrium carbonation by providing a gas reservoir above the liquid. After sealing containers, move to inspection. Fill level inspection checks for underfills and overfills. Cap inspection checks for missing caps and skewed caps. Seam inspection checks seam thickness and overlap on cans. Leak detection can identify micro leaks that would cause carbonation loss. Out of specification units are rejected automatically. If the product is packed into multi-packs, the sealed units are collated next. Cans can be wrapped in film or placed in cartons. Bottles can be grouped in shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heating is controlled so it shrinks film without overheating the beverage. Cartoning systems erect cartons and load units with gating systems that maintain spacing. Canada Dry Ginger Ale is manufactured by preparing a ginger citrus flavor syrup, blending it with treated chilled water at a fixed ratio, carbonating the beverage to a controlled dissolved CO2 level, then filling and sealing containers under counter pressure so carbonation and aroma remain stable. Production starts with water because it defines the baseline taste and the way carbonation behaves. Incoming water is filtered to remove suspended solids and then polished through fine filtration. Mineral content is adjusted to a target profile because hardness and alkalinity change perceived sharpness and sweetness. Water is then cooled because colder liquid absorbs CO more efficiently and reduces foaming at the filler. A sweetener stream is prepared in parallel. For sugar-based production, granulated sugar is dissolved in heated tanks with agitation until the syrup becomes clear. Syrup concentration is monitored by density because it determines final sweetness after dilution. The syrup is filtered to remove undissolved crystals that could clog valves and create settling. For alternative sweetener systems, a concentrated sweetener solution is prepared and handled as a metered liquid feed with stable density. The ginger flavor system is built as a concentrate that can be dosed precisely. Ginger character often includes both water-soluble notes and oil-based notes that need controlled dispersion. Flavor components are staged in small tanks and metered by weight into a blending vessel. Oil-based fractions are emulsified so they remain stable in the final beverage and do not separate in storage. High shear mixing reduces oil droplet size and improves emulsion stability. The concentrate is filtered to remove any particulate that could seed haze or block nozzles. Acid addition is managed as part of syrup formulation because pH controls brightness and stability. Acid is prepared as a liquid solution for accurate metering. It is injected into the syrup blend or into the flavor concentrate depending on line design. pH is measured and trimmed to a tight set point because small shifts change the ginger bite and the perceived sweetness. Buffer salts can be used in very small amounts to reduce drift, but the main lever is acid dose. If the formula uses a color system or a cloud system, those are handled as separate dosing streams. Color is held in tanks with gentle mixing and metered into the syrup at a controlled rate. Cloud systems are prepared as emulsions that remain suspended and carry aroma. Cloud emulsion. Stability is controlled by droplet size and by the choice of emulsifier. These streams are filtered and then injected into the syrup blend under controlled mixing. Once sweetener syrup and flavor concentrate and acid and any supporting streams are ready, they are combined into a finished syrup. Mixing is designed to create uniformity without entraining air. Air entrainment creates foam and reduces carbonation efficiency later. The finished syrup is held at a stable temperature to keep viscosity consistent for metering. It is delivered to the proportioning blender through metered pumps and protected by final inline filters. Final beverage blending is done with a proportioning system that meters syrup and chilled treated water. Control can be mass flow based or volumetric with density compensation. Ratio accuracy is the main determinant of consistent taste from run to run. The blended stream is monitored by inline soluble solids measurement as a proxy for syrup ratio. When solids drift, the control system adjusts valves to correct the ratio in real time. Before carbonation, the blended beverage is typically deaerated. Deaeration removes dissolved oxygen and entrained air. Oxygen can dull delicate ginger notes over time and can change aroma character during storage. Air also interferes with carbonation by promoting foam and reducing CO2 dissolution efficiency. Deaeration is performed under vacuum, where the liquid spreads as a thin film. Vacuum pulls gases out and the liquid exits with lower oxygen content. Carbonation follows deaeration and is controlled by temperature and pressure and contact efficiency. CO2 supply is filtered and regulated to stable pressure. The cold beverage enters a carbonator where CO2 is injected under pressure. Injection often uses a sintered stone or fine bubble injector to create small bubbles with high surface area. High surface area improves dissolution speed and reduces large bubble breakout. The carbonator maintains pressure high, enough to keep CO2 in solution. Dissolved CO2 is monitored continuously by instrumentation or by calculation from pressure and temperature. Temperature is a critical variable because CO2 solubility drops as temperature rises. The system compensates for temperature drift by adjusting pressure and by tightening cooling upstream. Stable chilling of water and blended beverage is therefore essential for consistent carbonation. Once carbonated, the beverage must be transported with minimal turbulence. Turbulence releases CO2 and creates foam, which leads to fill problems and carbonation loss. The line uses low shear pumps and smooth piping layouts. Sharp bends and sudden diameter changes are avoided. The product remains under pressure from carbonator through filler bowl to keep gas dissolved. Container handling runs in parallel with beverage preparation. Cans or bottles are conveyed and oriented and cleaned. Cans are typically rinsed and drained before entering the filler. Bottles are oriented and can be air rinsed or lightly rinsed, depending on line design. Plastic bottles may be supplied from blow molding and transferred quickly to avoid dust pickup. Container temperature matters because warm containers promote foaming. Staging is designed so containers do not heat excessively before filling. Filling uses counter-pressure equipment designed for carbonated beverages. Each container seals to a fill valve and is pressurized with CO2 to match the filler bowl pressure. Pressure equalization reduces turbulence when liquid enters. The fill valve opens and beverage flows in at a controlled rate. Fill level is controlled by a level probe or by timed flow depending on the filler type. Smooth flow is critical because foaming can cause underfills and messy seals. After the target fill level is reached, the valve closes and pressure is released in a controlled way. Controlled release prevents eruption and reduces foam at the top. Cans are then lidded and seamed immediately. Seam rollers form a tight double seam that locks the lid to the can body. Seam geometry is controlled by roller profiles and force because seam, overlap, and tightness determine leak resistance. Bottles are capped immediately with controlled torque. Torque control ensures sealing without damaging threads or liners. Headspace control supports carbonation retention and aroma stability. A defined headspace volume is left above the liquid. Many lines apply a CO2 jet just before sealing. This displaces air in the headspace and reduces oxygen pickup. Reduced oxygen helps keep the ginger aroma crisp during storage. Headspace CO2 also supports equilibrium between dissolved CO2 and gas phase CO2. Immediately after sealing containers, move through inspection. Fill level inspection checks for underfill and overfill. Closure inspection checks for missing caps or misapplied lids. Seam inspection on cans can include overlap checks and thickness checks. Leak detection can identify microleaks by pressure decay or vacuum methods. Out of tolerance units are rejected automatically to protect product consistency. If the product is produced in multiple packaging formats, the downstream handling changes slightly, but the goals remain the same. For multi-packs, cans are collated and wrapped in film or loaded into cartons. Bottles can be arranged into shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heat application is controlled so the film shrinks without overheating the beverage and driving CO2 loss. Cartons are erected and loaded with gating systems that maintain spacing and prevent scuffing. It all starts with malted barley, the soul of the beer. In a factory setting, the malt arrives by truckloads or freight trains already malted at a dedicated malting facility. Malting is a process in itself. Barley is soaked, allowed to germinate just enough to activate enzymes, and then dried and kilned to stop the growth. This controlled germination unlocks starches and enzymes that will later convert to fermentable sugars. The exact roast of the malt, pale, caramel, a chocolate, black, determines much of the final beer's color and flavor. For large-scale beers, base malts are used, usually lightly kilned, with small amounts of specialty malts blended in. The malt is piped into massive silos at the brewery, where it's stored dry and clean. When brewing begins, the malt is sent through a series of conveyors or airlifts to the mill. Here, roller mills crush the grain, not into flour, but into coarse grist. The idea is to crack the husk while leaving the interior accessible. Too fine, and the mash will become sticky and hard to filter. Too coarse, and sugar extraction drops. The grist is collected and weighed, then transported directly to the mash tun where the real transformation begins. In the mash tun, often a stainless steel vat the size of a swimming pool, the grist is mixed with hot water to form a thick porridge-like slurry. This step, called mashing, activates enzymes like amylase, which convert starches into simple sugars. The temperature is held precisely, usually around 65 and 68 degrees Celsius, depending on the style of beer. Too hot and the enzymes are denatured. Too cold and the starches won't fully convert. The mash is gently stirred using mechanical arms to ensure uniformity. For the next hour or so, the grain slowly transforms into a sweet liquid known as wort. When conversion is complete, the mash is transferred to the lautering vessel, sometimes built into the same tank. Lautering is the process of separating the liquid wort from the spent grain. A false bottom or fine slotted plates allow the liquid to drain through, while the grain bed itself acts as a natural filter. More hot water, known as sparge water, is sprayed over the top to rinse out every last bit of sugar. The collected wort flows to the brew kettle, while the spent grain, now protein-rich but sugar-poor, is conveyed out of the system. Many large breweries donate or sell this grain to farms as cattle feed. Next is the boil. In towering stainless steel kettles, the wort is brought to a rolling boil and held there for 60 to 90 minutes. This step sterilizes the liquid, halts enzymatic activity, and causes unwanted proteins to coagulate and fall out of suspension. It's also when hops are added. Hops are the cone-shaped flowers of the Humulus lupulus plant, prized for their bitterness, flavor, and aromatic oils. In a factory setting, hops usually arrive as compressed pellets for consistency. Early additions bring bitterness. Late additions and whirlpool hops contribute aroma and flavor. Boiling is carefully managed. A powerful steam jacket heats the vessel, while a system of condensers captures volatile compounds and steam vapor to reduce environmental impact. The smell during this stage is unmistakable. Sharp, herbal, sweet, and slightly pungent. It's the moment beer begins to take on its final character. After the boil, the wort must be rapidly cooled. This happens in a plate heat exchanger, where hot wort flows past cold water or glycol in alternating metal plates. Temperatures drop from near boiling to fermentation ready, usually between 10 degrees Celsius and 20 degrees Celsius, in just seconds. In most large breweries, the water used to cool the wort is captured and reused to preheat the next batch, conserving energy. From there, the chilled wort is transferred to fermentation tanks, colossal, conical bottom vessels made of polished stainless steel. Some are the size of small buildings. This is where the magic really happens. Yeast is introduced, either ale yeast or lager yeast. Yeast begins feeding on the sugars in the wort, producing alcohol and CO2 as byproducts. The tanks are fitted with sensors that monitor temperature, pressure, and gravity in real time. If fermentation is too vigorous, pressure is vented. If it's too slow, temperature can be nudged to wake up the yeast. Fermentation can last from a few days for ales to several weeks for lagers. During this time, brewers pull samples to test for alcohol levels, residual sugars, pH, and flavor development. In big factories, this data is fed into digital brewing systems that model yeast health and fermentation curves. If something's off, brewers are alerted immediately. Once fermentation is complete, the beer isn't quite ready. It must be conditioned, held at near freezing temperatures to clarify and stabilize. During this stage, yeast settles out, flavors mellow, and carbonation levels are adjusted. Some factories use centrifuges to speed clarification. Others rely on time and gravity. Filtration may be employed, either with diatomaceous earth, membranes, or cross-flow systems to remove fine particulates and ensure brilliant clarity. For beers that are meant to be bright and shelf-stable, pasteurization may follow, either flash pasteurization or tunnel pasteurization. But not all beer is pasteurized. Many craft-style or draft-only products skip this step to retain delicate aromas. Once the beer is bright, cold, and stable, it's ready for packaging. In large breweries, packaging lines are like choreographed metal highways. Bottling lines can run at 1,200 bottles per minute. Can lines are even faster. Kegs are cleaned, filled, capped, and labeled by machines. Bottles are rinsed, filled under pressure to avoid foaming, sealed with crown caps, and passed through date coders and labelers. Cans are seam locked, rinsed, and pressure checked. Every container is sampled for fill height, oxygen pickup, carbonation, and microbial safety. In some facilities, advanced cameras scan every bottle or can for imperfections in milliseconds. The packaging halls are cold, loud, and almost hypnotic. Conveyor belts twist and curve. Robotic arms stack cases onto pallets. Shrink wrap machines seal entire loads for distribution. Forklifts or automated guided vehicles shuttle product to cold storage, where beer awaits distribution to bars, grocery stores, sports stadiums, and corner shops around the world. But behind the machinery is a deeper layer of quality assurance. Beer is a living product, and even at massive scale, breweries run labs that would rival pharmaceutical facilities. There are microbial labs, sensory panels, gas chromatographs, and mass spectrometers analyzing aroma compounds, esters, sulfur levels, and oxygen ingress. Trained tasters, often called sensory analysts, taste beer daily, blind, and score it against reference samples. A slight change in carbonation or hop aroma is enough to flag a batch for review. And hygiene is non-negotiable. Brewing equipment is cleaned constantly with clean-in-place systems that circulate caustic solutions, acid rinses, and sanitizers through every pipe, pump, tank, and valve. Breweries are designed with sloped floors, airlocks, positive pressure rooms, and filtered ventilation to minimize contamination. Yeast cultures are kept in pure, cryogenically preserved banks and propagated in sterile fermenters. Even the water is treated, filtered, softened, and dechlorinated to ensure it doesn't introduce off flavors. Despite the scale, there's a strange elegance to the whole system. Every tank, pump, sensor, and pipe is part of a carefully designed loop. From raw grain to finished beer, the factory operates almost like an ecosystem, closed, balanced, and tightly monitored. Nothing is left to chance. Even the CO2 released during fermentation is often captured and reused to carbonate the final product, reducing waste and environmental impact. Bacardi all starts with molasses, a byproduct of sugar refining. Once cane juice has been boiled and crystallized into sugar, what remains is a dark, viscous liquid rich in residual sugars and minerals. Bacardi sources its molasses primarily from the Caribbean and Central America, where sugarcane grows in abundance. Shipments arrive by the ton, offloaded into deep storage tanks that keep the molasses warm and pumpable. Its smell is rich and heavy, deeply sweet, slightly sour, with a roasted, almost smoky undertone. Before fermentation begins, the molasses is diluted with pure water and combined with nutrients to prepare what's known as the fermentation wash. Bacardi uses a proprietary strain of yeast, one that's been carefully preserved and propagated for generations. This yeast is key. It's what gives Bacardi its distinctive profile: clean, light, with subtle fruity esters and very low levels of fusel oils. In a dedicated propagation room, yeast cells are grown in increasingly larger vessels, fed on molasses and oxygen, until they're strong enough to handle full-scale fermentation. The prepared wash, diluted molasses, nutrients, and yeast is pumped into fermentation tanks, towering steel vessels the size of small silos. Fermentation is fast and efficient, typically 24 to 30 hours. During that time, the yeast devours the sugars, converting them into alcohol and CO2. The temperature is carefully regulated. Too hot, and the yeast dies. Too cold, and it underperforms. Sensors monitor every parameter in real time: sugar levels, temperature, pH, alcohol content. In massive control rooms, technicians watch digital dashboards as each tank ferments with machine-like consistency. The result of this stage is not rum yet. It's a low alcohol liquid called wash or beer, usually around 7 to 10% ABV. It smells nothing like rum. It's sweet, funky, raw. To transform it into the clear, potent spirit known around the world, Bacardi moves to the next phase: distillation. Distillation is where alcohol is concentrated and flavors are defined. Bacardi doesn't rely on pot stills, as many small batch rums do. Instead, it uses continuous column stills, tall, multi-stage distillation towers that can separate alcohol with incredible precision. These columns have trays or packing materials inside that force the vapor and liquid to interact repeatedly, concentrating the alcohol while removing unwanted compounds. The fermented wash is pumped into the column, heated from the bottom, and as it rises, different components evaporate at different heights. Light, clean alcohols rise to the top and are collected. Heavier compounds are left behind and drained off. By adjusting the temperatures and reflux ratios, Bacardi's distillers control the exact cut of alcohol they want to keep. The result is a high-strength spirit, often 85% ABV or higher, that's clear, light, and extremely pure, essential for Bacardi's signature smoothness. But pure alcohol isn't rum yet. The next steps, aging, blending, and finishing, are where the artistry comes in. The raw distillate, also called aguardiente, is diluted down to around 60 to 70% ABV and pumped into oak barrels for aging. Bacardi primarily uses used American white oak barrels, many of which once held bourbon. These barrels are charred on the inside, and over time, they impart color, vanilla notes, spice, and tannins to the rum. In Bacardi's aging warehouses, massive barrel halls with racks stacked to the ceiling. Tens of thousands of casks rest in the tropical heat. The climate speeds the interaction between spirit and wood, making even short aging periods highly effective. Different rums are aged for different durations. Bacardi Superior, the classic white rum, may be aged for as little as 1 year before being filtered. Gold and flavored varieties rest longer. Premium products like Bacardi 8 or Bacardi Reserva Limitada are aged 8 to 12 years or more. Each barrel breathes. Alcohol evaporates, a phenomenon known as the angel share, and oxygen seeps in. Over time, harsh edges soften, flavors deepen, and the rum becomes increasingly complex. Once aging is complete, barrels are emptied, and the rum is evaluated. This is where Bacardi's master blenders, trained experts who can detect flavor differences down to the subtlest note, step in. Dozens, sometimes hundreds of barrels are selected and blended together to create a final product with exactly the right profile. Some rums bring fruity notes, Others deliver weight or spice. Others still provide structure or sweetness. The blender's job is to make the sum better than the parts, and to ensure that every bottle tastes exactly like the last one, year after year. Now comes one of Bacardi's most distinctive processes, charcoal filtration. For Bacardi Superior and other light rums, the blended rum is passed through layers of activated charcoal, often made from coconut husks, to remove color and certain heavy flavor compounds. This process, inspired by Don Facundo Bacardi himself in the 1860s, strips away rough edges and leaves the rum bright, clean, and smooth. Even after aging in oak, the charcoal returns the rum to a near-clear appearance while preserving its vanilla and almond undertones. Once filtered, the rum is diluted with ultra-pure demineralized water down to bottling strength, usually 37.5% or 40% ABV, depending on the market. It's then passed through fine mesh filters to remove any remaining particles, chilled to encourage clarity, and tested for stability. Quality checks are constant. ABV, color, turbidity, aroma, flavor, all are measured in both labs and sensory rooms. Finally, the rum is ready to be bottled. Bacardi's bottling lines are massive, high-speed operations, capable of producing tens of thousands of bottles per hour. Empty glass bottles, custom-shaped with embossed bats and logos, are automatically loaded onto conveyors. They're rinsed, filled with rum under pressure, sealed with tamper-proof caps, and labeled with laser precision. Date codes are printed, barcodes are verified. Every bottle passes through inspection tunnels equipped with cameras and sensors to catch defects, underfills, or misplaced labels. From there, bottles are packed into cartons by robotic arms and shrink-wrapped onto pallets. Pallets are barcoded, logged, and stacked in warehouse zones ready for distribution. Bacardi's logistics network spans continents. From a single facility, trucks, ships, and containers move product across the globe. To supermarkets in Spain, beach bars in Brazil, nightclubs in New York, and resorts in Thailand. Behind the scenes, sustainability plays an increasing role. Many of Bacardi's distilleries use renewable energy, recycle processed water, and recover CO2 from fermentation. Spent yeast and distillation byproducts are often converted into animal feed or used in bioenergy systems. Even the barrels, when retired, may be repurposed for furniture, flooring, or smaller barrel aging projects. Waste reduction is not just about economics. It's part of preserving the legacy of the land and the product itself. And yet, for all this technology and scale, Bacardi's rum still carries with it a certain history, a sense of origin. The company was founded in 1862, and though exiled from Cuba in the 1960s, its roots remain in the tropics. The smoothness of Bacardi rum isn't just a technical achievement, it's a philosophy. Every step, from selecting molasses to filtering the final spirit, is guided by an obsession with drinkability. A Bacardi rum should be mixable, approachable, and endlessly clean on the palate. Jack Daniel's begins with a precisely controlled mash bill of 80% corn, 12% malted barley, and 8% rye. The grains arrive in massive quantities by rail and truck, and are stored in silos before being milled on-site in Lynchburg, Tennessee. Corn is cracked into coarse grits. Malted barley and rye are milled finer. The grain is moved pneumatically into huge stainless steel cookers where it undergoes a staged cooking process. Corn first, cooked at a high temperature to gelatinize the starches, then rye, then finally malted barley is added as the mash cools to around 65 degrees Celsius. The malt's enzymes convert starches into fermentable sugars. The resulting mash is pumped into one of 64 fermentation vats. Open-top tanks made from cypress wood, some more than 80 years old. These vats each hold around 40,000 gallons. Jack Daniel's uses its own proprietary yeast strain, maintained and propagated internally since the early 20th century. Before yeast is pitched, a portion of the previous day's fermented mash is added to the new batch. This sour mash technique helps control the pH and microbial stability of the fermentation environment. Yeast is pitched in liquid form and begins consuming sugars, producing ethanol and CO2. Fermentation lasts 4 to 6 days. The mash foams, bubbles, and gives off heat. During peak fermentation, tanks require constant monitoring for overflow and contamination. Automated sensors track sugar depletion, CO2 output, and temperature curves. Staff monitor the aroma, foam height, and microbial activity daily. When fermentation is complete, the liquid contains roughly 7-9% alcohol by volume. This distiller's beer is pumped into column stills, massive stainless steel and copper columns more than 40 feet tall. Jack Daniel's uses a single-stage continuous distillation process. Beer enters the column at various levels, while steam is injected from below. Alcohol vapor rises, separating from heavier components. The alcohol vapor is routed to a doubler, essentially a pot still operating at atmospheric pressure, where it's condensed, reheated, and distilled again. The resulting clear spirit, often referred to as White Dog, emerges at around 140 proof. Before aging, Jack Daniel's performs its most defining step, the Lincoln County process, or charcoal mellowing. This process takes place in vats over 10 feet tall, filled with sugar maple charcoal. The charcoal is made on-site by stacking 2x2-inch thick maple planks into long rows, igniting them with high-proof whiskey and letting them smolder until fully carbonized. Once cooled, the charcoal is ground into chunks and loaded into mellowing vats. The White Dog is slowly trickled, drip by drip, through 10 feet of charcoal, taking 4 to 5 days to pass completely through. The charcoal removes fusel oils, aldehydes, and other harsh flavor compounds. The process is gravity-fed and unpressurized, requiring a consistent flow rate to maintain quality. The resulting spirit retains its proof, but emerges smoother and cleaner, with noticeably reduced volatility. Once mellowed, the whiskey is moved into new, charred American white oak barrels, coopered at Jack Daniel's own barrel-making facility. The staves are air-seasoned outdoors for 6 months to 2 years, then assembled, toasted, and flame-charred to a specific level designed to maximize flavor extraction and color development. Each barrel holds about 53 gallons. The inside is blackened from charring, and the wood sugars have caramelized. Barrels are filled at 125 proof and rolled into one of 90-plus barrel houses across the Lynchburg area. These rickhouses vary in size and construction. Some are multi-story wood frame structures, others are steel-clad, but all use passive temperature variation to promote aging. Inside the barrel house, environmental conditions vary dramatically. Upper floors reach 100-degree F+ in summer, encouraging evaporation and faster aging. Lower levels remain cooler and more stable. Jack Daniel's does not rotate barrels between floors, so aging is not uniform. Instead, blending later equalizes the flavor profiles. Barrels are stacked on wooden ricks, often 6 to 7 high. During aging, the whiskey interacts with the wood. Alcohol penetrates the staves, extracting vanillin, lignin-derived compounds, tannins, and hemicellulose breakdown products like caramelized sugars. Oxidation occurs gradually as oxygen seeps through the porous wood. Angel's share evaporation causes the proof to rise over time and concentrates the flavor. Each year, a barrel loses 2-5% of its volume to evaporation. Maturation time varies by product. Old No. 7 typically ages for 4 to 6 years. Higher end expressions like Single Barrel or Sinatra Select may rest for up to 8 years or more. Throughout aging, barrels are sampled periodically. Staff draw whiskey using a thief and assess it by color, aroma, proof, and mouthfeel. No age statement is printed on standard Jack Daniel's because, Blending is used to maintain consistency, not target a specific age. When deemed mature, barrels are dumped onto a stainless steel trough, filtered through mesh screens to catch char, and moved to batching tanks. Here, up to 200 barrels are blended into a single batch. Before bottling, the whiskey is chill filtered, cooled to near freezing, and passed through paper or cellulose filters to remove fatty acid esters that can cause clouding in the bottle. For Old Number 7, the spirit is then diluted to 80 proof, using demineralized water drawn from the same cave spring used for mashing. Other products, like bonded or single barrel proof, may be bottled at higher strengths or without filtration, depending on the release. Bottling takes place on high-speed automated lines. Empty bottles are rinsed with pressurized air or filtered water. Filling machines dispense whiskey using gravity-fed nozzles or vacuum-assisted pumps. Bottles are capped with aluminum closures, corks, or synthetic caps depending on the SKU. Labels are applied using roll-fed labelers with electronic eyes that verify positioning. Lot codes and production dates are printed in UV ink or laser etched onto the neck. Every bottle passes under fill level sensors and automated cameras. Defective units are ejected immediately. Bottles are grouped into cases, shrink-wrapped, and palletized by robotic arms. Finished goods are transported to climate-controlled warehouses. Logistics teams track SKU distribution globally. Jack Daniel's is shipped to more than 170 countries. Each batch must meet regional regulatory standards. Export whiskey may require separate bottling or labeling runs to comply with EU, UK, or Asian labeling laws. Quality control labs sample bottles from each run and perform gas chromatography and spectrophotometry to confirm chemical composition. Sensory analysts run blind tastings daily to validate flavor accuracy. Any deviation from the flavor profile, too much wood, too much sweetness, excessive ethanol burn, results in a hold or rework. Spent grain from mashing is pumped to presses, dried, and sold as cattle feed. Wastewater is treated on-site using anaerobic digesters and aerobic ponds before being discharged or reused. Energy recovery systems capture steam from cooking and distillation to heat water for fermentation tanks. Charcoal from the mellowing vats is replaced regularly and either regenerated or disposed of as biomass fuel. Spent barrels are sold to Scotch distilleries, hot sauce producers, and breweries for secondary use. The cooperage also reconditions barrels for use in cask-finished products or special editions. The distillery operates under strict federal and state regulation. Every barrel and bottle is tracked with a unique serial number. Auditors inspect warehouse records, bottling logs, and inventory counts. The distillery maintains TTB-compliant records for every production step, from raw grain receipt to final export certificate. Barcodes and RFID tags on pallets ensure traceability from distillation to retail shelf. Security is tight, bonded warehouses are sealed, and access is controlled. Jack Daniel's uses SAP-based systems for production scheduling, batch tracking, and global inventory management. Brewing, fermentation, and distillation data are logged automatically by PLCs connected to SCADA systems. Operators monitor process parameters in real time on touchscreen interfaces. Alerts are triggered if mash temperature, fermenter pressure, still output, or bottling line speed moves out of range. Scheduled maintenance is performed weekly. Sensors check flow rates, valve positions, CIP cycle effectiveness, and tank volumes continuously. Yeast propagation is handled in a sterile lab with HEPA-filtered air, jacketed tanks, and strict aseptic technique. Each batch of yeast is cryogenically preserved and banked in long-term storage. Lab staff test yeast for viability, contamination, and fermentation performance. Infection events, such as wild yeast or lactic acid bacteria, are rare but can halt production for full CIP sanitization of all affected equipment. Sanitizers include caustic soda, peracetic acid, and steam. Safety inspections and confined space protocols are rigorously enforced, especially around fermentation tanks, high-pressure steam lines, and ethanol vapor zones. Mash cookers and fermentation tanks are cleaned between every batch. Distillation columns are stripped and acid washed quarterly. Mellowing vats are emptied and replenished every few months. Barrels are inspected for leaks before filling. Leakers are flagged and re-co-opted or discarded. Every floor drain, gasket, and pump seal is part of a scheduled inspection checklist. The entire facility is USDA certified for food safety and operates under HACCP protocols. Coca-Cola starts with treated water. Incoming water passes through filters that remove suspended particles. It may move through activated carbon beds, ion exchange systems, and fine membrane filters. These stages produce water with a consistent mineral profile, taste, and clarity. The treated water enters stainless steel storage tanks. The tanks are sealed and fitted with sensors that monitor level, temperature, flow, and pressure. From there, pumps send the water toward the syrup room. In the syrup room, granulated sugar or liquid sweetener is measured into a mixing tank. Warm treated water is added to help dissolve it. Large agitators turn inside the tank, pulling the sweetener downward and folding it back through the liquid. The surface changes from cloudy and grainy to smooth and clear. The syrup is filtered again to remove any undissolved particles. It then moves into another stainless steel vessel, where Coca-Cola concentrate is added. The concentrate contains the flavoring system and caramel color. It is dosed in carefully controlled amounts. Flow meters and load cells measure the addition with high precision. The concentrate enters as a dark stream and spreads through the syrup as the agitator spins. The mixture becomes a finished syrup. It is dense, glossy, and intensely flavored. It is not yet the final drink. It still needs to be diluted with treated water and carbonated. Before blending, the syrup may pass through a deaeration step. Removing excess oxygen helps protect the flavor and improves carbonation performance. A vacuum chamber pulls dissolved gases out of the liquid. Tiny bubbles rise and collapse as the pressure drops. The finished syrup is pumped to a proportioning unit. This machine combines syrup and treated water at a fixed ratio. The two streams enter through separate pipes and meet inside a blending chamber. Sensors check flow rate continuously. Automatic valves make small corrections so the mixture stays uniform. The blended Coca-Cola then moves toward the carbonation system. Carbon dioxide is fed from pressurized storage. The gas is filtered and regulated before it reaches the carbonator. The beverage is chilled because cold liquid absorbs carbon dioxide more efficiently. Heat exchangers lower the temperature quickly as the liquid flows through thin channels or tubes. Inside the carbonator, the chilled beverage meets carbon dioxide under pressure. The gas dissolves into the liquid, forming the sharp, sparkling texture of the finished drink. The system keeps the beverage enclosed so the carbonation stays locked in. The carbonated Coca-Cola is now ready for filling. On a plastic bottle line, PET preforms may be made or supplied separately. These preforms look like small, thick test tubes with finished neck threads. They are heated in an oven with infrared lamps until the plastic softens. The preforms then enter a blow molding machine. Each hot preform is clamped inside a bottle mold. A stretch rod pushes downward, extending the plastic. Compressed air bursts into the preform, forcing it outward against the mold walls. In less than a second, the small tube becomes a full-size bottle. The mold opens and the bottle emerges warm, clear, and rigid. For glass bottles, formed bottles arrive already molded. They pass through inspection systems that check shape, cracks, chips, and contamination. Light beams and cameras examine the mouth, base, sidewall, and interior. Any defective bottle is pushed off the line automatically. Cans follow a different path. Aluminum cans arrive open at the top and move through air rinses. They are inverted, blasted clean, and returned upright before filling. The filling machine is the fastest and most precise stage. Bottles or cans enter a rotating filler with dozens or even hundreds of filling valves. Each container lifts toward a valve. The valve seals against the opening. Pressure inside the container is balanced with the pressure in the filler bowl. This prevents foam from erupting when the carbonated drink enters. The liquid flows down the container wall in a controlled stream. Filling is measured by level, volume, or mass, depending on the system. The container reaches the exact fill height, the valve closes, and the container moves away. The sound is continuous and rhythmic. Clinking glass, humming motors, clicking star wheels, and short bursts of gas pressure. Immediately after filling, the container is sealed. Plastic bottles pass under a capper. Caps are sorted in a bowl feeder, lined up in a chute, and delivered one by one to the capping heads. Each head picks up a cap, places it on the bottleneck, and twists it to a specified torque. The tamper band locks beneath the neck ring. Glass bottles may receive crown caps. A capping head presses the metal crown over the lip of the bottle. The ridged edge folds tightly under the glass bead, creating a gas-tight seal. Cans go to a seamer. A lid is placed on top of each filled can. The can spins, while seaming rolls curl the lid edge and can flange together. The metal folds into a tight double seam that holds carbonation under pressure. After sealing, the containers pass through inspection. Fill level sensors check whether each bottle or can contains the correct amount. Cap inspection cameras verify position, angle, and seal presence. Pressure or vacuum detectors check closure integrity. Label sensors, code readers, and vision systems examine alignment and printed marks. Any container outside tolerance is rejected by a fast pneumatic arm or air jet. It leaves the mainstream without slowing the rest of the line. The sealed Coca-Cola then moves toward labeling. Plastic bottles may pass through a roll-fed labeler. A thin printed film unwinds from a roll and is cut into individual labels. A small strip of adhesive is applied to the leading and trailing edges. The label wraps around the bottle as it rotates against a drum. Other bottles receive pressure-sensitive labels. These peel from a backing web and press onto the container surface with foam rollers. The rollers smooth the label so it follows the bottle's curve without wrinkles. Glass bottles may receive paper labels with cold glue. The labeler picks up each label, coats it with adhesive, and presses it onto the glass. Brushes wipe the label flat as the bottle spins. For cans, decoration is usually printed directly onto the aluminum before filling. After sealing, cans still receive a date code and batch code. Coding machines apply production information to each container. Inkjet printers spray tiny droplets onto the cap, shoulder, base, or can bottom. Laser coders may etch the mark into the surface. The code is brief, sharp, and traceable. The containers then pass through drying tunnels or air knives. High-speed air strips away condensation and rinse water. This gives the surface enough dryness for packaging equipment to handle it cleanly. Next comes grouping. Bottles travel into lanes formed by guide rails. Timing screws separate them into exact spacing. The machine gathers them into packs of 6, 12, or another format. Colliders push the bottles into rectangular patterns. For shrink-wrapped packs, a sheet of plastic film wraps around the group. The pack enters a heat tunnel. Hot air shrinks the film tightly around the bottles. The plastic grips the shoulders and bases, forming a compact bundle. For cardboard cartons, flat blanks feed from a magazine. The machine opens or folds the board around the bottles or cans. Glue nozzles apply hot melt adhesive. Compression belts press the flaps until the glue sets. Cans may be packed into trays. A corrugated sheet folds upward around the base of the group. The tray holds the can steady while film wraps over it or while the open tray moves directly to palletizing. The finished packs travel along conveyors to the palletizer. Cases are turned, aligned, and arranged into layers. A robotic arm or gantry system lifts each layer and places it onto a pallet. Sheets of cardboard may be inserted between layers to stabilize the stack. The pattern changes from one layer to the next so the load locks together. Fanta production begins with orange syrup, forming inside a closed stainless steel tank. Treated water enters first. It has already passed through filtration, activated carbon, and polishing stages to remove particles, odors, and unwanted mineral variation. This gives the drink a neutral base before any flavor is added. A measured amount of this water flows into the syrup tank. The agitator starts slowly, then builds a steady rotation. The blades pull the liquid downward and push it outward against the tank wall, creating a smooth, rolling motion. Sweetener is added into the moving water. In some plants, it is granulated sugar. In others, it is liquid sugar or another approved sweetener system. If dry sugar is used, the crystals fall into the vortex and begin dissolving. The liquid turns slightly cloudy at first, then becomes clearer and heavier as the sweetener fully blends in. Warmth may be applied through the tank jacket or an inline heating system. The heat helps the sweetener dissolve faster and keeps the syrup consistent. The mixture thickens, reflecting light in slow waves as the agitator turns. The sweet syrup is filtered before flavoring. It passes through fine filters that catch undissolved particles. This protects the later equipment, especially flow meters, proportioning valves, and filling heads. The filtered syrup moves into a second blending tank. This is where Fanta begins to separate from cola production. Cola syrup is dark, spicy, and caramel heavy. Fanta syrup is brighter, fruitier, and usually built around citrus flavor, acidity, color, and sometimes a clouding system. Orange flavor concentrate is dosed into the sweet syrup through closed lines. Metering pumps control the amount precisely. A small volume of concentrate flavors a much larger volume of syrup, so the dosing must stay exact. The concentrate enters below the surface of the liquid. It disappears into the moving syrup and spreads through the tank. The agitator keeps the mixture uniform, preventing strong pockets of flavor from forming. Color is added as part of the concentrate system or as a separate ingredient, depending on the formula. The syrup shifts from pale yellow to a dense orange tone. It looks much stronger than the final drink because it has not yet been diluted. Acid is blended next. Orange soda needs a sharp citrus edge to balance its sweetness. Citric acid is commonly used because it creates a bright, fruit-like bite. The acid dissolves into the syrup until the flavor base reaches the required balance. Some Fanta formulas include emulsified citrus oils. Citrus oils do not naturally mix with water, so they must be dispersed into tiny droplets and held in suspension. Stabilizers keep the droplets evenly distributed. This gives the drink a fuller, slightly cloudy appearance instead of a perfectly clear look. The mixing speed matters at this stage. Too little movement leaves uneven flavor. Too much shear can damage the emulsion structure. The tank keeps the syrup moving with controlled force, enough to blend, but not enough to break the system. The finished syrup is dense, sweet, acidic, aromatic, and strongly colored. It is not yet drinkable. It is a concentrated base that must be diluted with treated water. The syrup flows toward the proportioning unit. A separate stream of treated water arrives from storage tanks. Both streams pass through flow meters. The proportioner continuously compares the syrup flow with the water flow. The machine adjusts valves in real time. If the water flow rises, the syrup feed changes with it. If syrup pressure drops, the system corrects the ratio. The goal is a constant blend from the first bottle to the last. Inside the blending chamber, the thick orange syrup meets the treated water. The color brightens. The texture becomes lighter. The flavor spreads through the full liquid volume. At this point, the drink looks close to finished Fanta, but it is still flat. Before carbonation, the liquid is chilled. The beverage passes through a heat exchanger made of thin metal plates or tubes. Cold glycol or another cooling medium runs on the opposite side. Heat moves out of the drink quickly while the liquid remains sealed inside the system. Cold liquid absorbs carbon dioxide better than warm liquid. This step also helps reduce foam during filling. If the beverage were too warm, it would release gas too quickly and fill unevenly. The chilled liquid may pass through a deaeration stage. A vacuum chamber pulls dissolved air out of the beverage. Tiny bubbles rise and collapse as the pressure drops. Removing excess oxygen helps the flavor stay stable and prepares the drink for carbonation. Carbon dioxide arrives from pressurized storage. Regulators reduce and control the gas pressure. The gas passes through filters before entering the carbonator. Inside the carbonator, the chilled Fanta meets carbon dioxide under pressure. The gas dissolves into the liquid. It does not simply bubble through and escape. Pressure, temperature, and flow are balanced, so the carbonation stays locked inside the drink. While the liquid is being prepared, the containers move through their own production path. For plastic bottles, PET preforms are fed into a heating oven. Each preform looks like a thick test tube with finished neck threads. Infrared lamps soften the plastic while the preforms rotate so the heat spreads evenly. A transfer wheel carries each hot preform into a mold. The mold closes around it. A stretch rod pushes down through the center, pulling the plastic lengthwise. Then, compressed air blasts inside the preform. The softened plastic expands against the mold wall. The bottle shape appears almost instantly, including the base, shoulders, grip panels, and label area. The mold opens and the new bottle moves out, still warm and clear. If glass bottles are used, they arrive already formed. They pass through inspection before filling. Cameras and light beams check the mouth, sidewall, base, and interior. Cracked, chipped, dirty, or misshaped bottles are rejected automatically. If cans are used, empty aluminum cans arrive open at the top. They pass through an air rinser. Each can is inverted, blasted with filtered air, and turned upright again before filling. The filler brings the finished drink and the container together. Fanta is carbonated, so the filling machine must control pressure carefully. Containers enter through a star wheel and move beneath filling valves. Each container seals against a valve. Pressure is equalized before liquid enters. The orange drink flows into the container in a controlled stream. It is guided to reduce turbulence and foam. The liquid rises smoothly from the bottom until it reaches the correct level. The valve closes immediately after the target fill is reached. The container leaves the filler and moves straight to sealing. Plastic bottles pass under a capper. Caps are sorted, lined up, and delivered to rotating capping heads. Each head places a cap on the bottle and tightens it to a set torque. The tamper band locks below the neck ring. Glass bottles receive crown caps. A metal crown is pressed over the mouth and crimped under the glass bead. Cans move to a seamer, where a lid is placed on top and folded into a tight double seam. Raw onions become a consistent retail product inside a packing facility by being dried and stabilized, cleaned, graded by size and quality, trimmed, cured if needed, then packed under airflow conditions that preserve firmness and limit sprouting. The process starts with bulk bins, entering a receiving line designed for a crop that bruises less than fruit but still damages easily at neck and scale layers. Bins are tipped onto a receiving conveyor with controlled drop height. The infeed spreads onions into a single moving layer, so downstream cleaning is uniform. Conveyors use flights and side guides to prevent rolling pileups that can crack outer skins. Field material is removed early. The onions pass through a scalper where loose soil, stones, and plant fragments fall through screens. A parallel air separation stage lifts light chaff and dry tops away from the heavier bulbs. This early separation protects later brushing and sizing equipment from abrasion and reduces dust load inside the plant. Curing or conditioning is a central step for raw onions because outer skins and neck tissue must be dry before long storage and retail packing. If onions arrive partially cured, they still often enter a forced air curing tunnel. In a curing tunnel, onions sit in bins or flow through a bed while warm, dry air moves through them. Air temperature is controlled so it dries skins without cooking the bulb. Air humidity is controlled so drying continues efficiently. Airflow is designed to move through the pile rather than around it because onion drying is limited by how fast moisture leaves the neck and outer scales. Curing targets a dry neck and a tight, papery outer skin. A dry neck reduces rot risk and reduces sprouting. A tight skin protects the bulb during later handling and provides the familiar dry onion appearance. Curing duration depends on incoming moisture and bulb size, but the technical goal is consistent moisture at the outer layers so later brushing does not peel too deeply. After curing, the onions move into cleaning. Cleaning focuses on removing loose skins and soil while keeping enough skin to protect the bulb. Rotary brushes scrub the surface and loosen brittle outer layers. Brush stiffness and speed are tuned so skins shed without gouging. A counter-rotating brush bank can be used to lift skins at multiple angles. Dust extraction hoods remove the shed skins and dry dust. Dust removal is important because airborne skins can clog screens and contaminate weighing systems. Roots and tops are handled next, depending on how the onions arrived. Some onions enter with tops already removed. Others enter with dried tops still attached. A topper cuts the neck to a specified length. Cut length is controlled because too long creates tangles in bagging and too short exposes moist neck tissue. A root trimmer removes roots flush with the basal plate without cutting into the plate. Cutting into the basal plate increases decay risk. Trimming systems use rotating blades or abrasion heads with guides that center the bulb. After trimming the onions, pass through a second cleaning stage. This stage removes fragments created by topping and root trimming. A combination of brushes and air knives lifts loose skins. Screens remove small fragments and soil. The line aims to deliver a clean bulb with intact protective skins. Sizing and grading follow. Onions are graded primarily by diameter and by external quality. Diameter sizing is done with roller sizers, belt sizers, or optical measurement systems. In roller sizing, the gap between rollers increases along the machine. Smaller onions fall through earlier gaps and larger onions ride further. This creates size classes for different retail packs. Optical sizing uses cameras to measure diameter as onions roll. The measured size triggers diverters that route onions to dedicated lanes. Quality grading is added to remove defects that would fail retail standards. Optical systems can detect bruises, cuts, mold, rot, and excessive skin loss. They can also detect green necks and splits. Split bulbs are a defect because they break down quickly and do not pack well. Sorting can be done with air jets or gates that remove defective bulbs from the flow. For defects that are hard to see externally, some lines use density-based methods or near-infrared sensing to estimate internal issues, but the main control remains external defect removal and dry neck verification. After grading, onions often enter a polishing step. Polishing uses softer brushes to smooth the outer skin and improve appearance. The goal is not shine like waxed fruit, but uniform skin and removal of remaining loose flakes. Polishing also reduces the amount of loose skin that ends up in bags. At this point, the line splits into multiple packing formats. One route is loose bulk cartons for food service and wholesale. Another route is consumer bags in specific weights. Another route is small tray packs or mesh sleeves. For bulk cartons, onions feed into a carton filler that drops bulbs in layers. Drop height is controlled to prevent bruising at the basal plate. Cartons are sized to the onion class. A pad can be used to reduce abrasion during transport. Cartons are closed and taped. Codes are printed for traceability. Weight checks confirm cartons meet target gross weight. For consumer bags, onions are portioned by weight. A weigher accumulates onions until target weight is reached. The portion drops into a bag former. Bags can be mesh for airflow or film with perforations. Mesh is common because onions need ventilation. Bagging equipment forms and seals the bag. Seal timing is set so no onion sits in the seal zone. A tag or label is applied. Bags are then collated into cases or onto trays. For small net sleeves, the line uses a sleeve applicator that stretches a tubular net over a set of onions. A clip seals both ends. This format demands tight size control, so the sleeve tension stays consistent and does not crush bulbs. Throughout packing, ventilation is treated as a product requirement. Onions release moisture and gases during storage. Packages therefore include ventilation holes or mesh to reduce condensation. Cases are designed with vents aligned to allow airflow through stacks. This airflow helps keep bulbs dry and slows sprout development. Storage and staging are integrated into the packing workflow. Packed onions may be held in cool, dry rooms before shipping. Temperature is held low enough to slow sprouting, but not so low that skins become brittle and crack during handling. Humidity is controlled because high humidity softens skins and encourages decay. Low humidity dries skins further but can increase skin flaking. Airflow is used to keep conditions uniform through stacked pallets. If onions are destined for longer storage before packing, the facility uses bulk storage bins with forced air ventilation. Onions are loaded into large bins and air is pushed through to remove residual moisture and to maintain temperature. Sprout suppression can be part of the broader supply chain strategy, but the mechanical packing process relies primarily on curing, temperature control, and ventilation. A separate route exists for peeled raw onions used in food service. In this route, onions are graded and then sent to peeling equipment. Peeling begins with scoring the outer skin and then using air blasts to lift skins away. A mechanical peeler can roll the onion against abrasive surfaces to remove outer layers. The peeled onions are then washed to remove skin fragments and drained. Trimming removes remaining root plate fragments and neck tissue. Peeled onions are then sized and packed in bags with controlled drainage. This route requires tight sanitation control and cold handling, but the core mechanical steps are scoring, peeling, washing, trimming, and draining. Garlic becomes a consistent retail product inside a packing facility by being cured to stabilize skins and cloves, cleaned, trimmed, graded by size and quality, then packed in ventilated formats that preserve dryness and limit sprouting. The process begins when bulk bins or totes of garlic enter the receiving line. The first objective is to move the bulbs from field containers into a controlled flow without tearing skins or snapping necks. Hydraulic bin tippers discharge garlic onto cushioned conveyors with low drop heights. Side guides spread bulbs into a single layer, so cleaning and grading equipment sees each bulb rather than a pile. Conveyor speeds are set to avoid rollback that cracks outer wrappers. Field debris is removed early because dry leaves and soil create dust that interferes with sizing and increases abrasion. Garlic passes over scalping screens where loose soil and small stones drop through. An air separation stage lifts light dried tops and chaff away from the heavier bulbs. Dust extraction hoods capture fine particles, so they do not circulate and settle on sensors and belts. Curing is a central garlic-specific step because long storage performance depends on drying the neck and tightening outer skins. If garlic arrives partially cured, it still typically enters forced air curing tunnels or bulk curing rooms. Bulbs are loaded into ventilated bins or spread in shallow beds. Warm, dry air is pushed through the mass. Air temperature is controlled so moisture leaves quickly without softening cloves. Air humidity is controlled so drying potential stays high. Airflow is directed through the pile rather than over it because neck drying is limited by how fast air can. Remove moisture at the bulb surface. Curing targets several physical outcomes. Outer wrappers become papery and resistant to abrasion. The neck dries and seals, so microbes and moisture cannot travel into the bulb. Cloves stabilize and become firm rather than watery. Curing time is tuned based on bulb size and initial moisture. The facility monitors outlet air humidity and bulb wrapper feel as process indicators. The objective is a stable dry bulb that can be brushed and trimmed without tearing deep layers. After curing, garlic enters cleaning, where the goal is to remove loose skins and soil while keeping enough wrapper layers to protect the cloves. Brush beds rotate the bulbs and sweep away brittle outer skins. Brush stiffness is chosen to avoid scuffing that exposes cloves. Brush speed is tuned so bulbs roll and contact brushes evenly rather than sliding. Air knives and aspiration remove loosened skins from the stream. Skin removal is controlled because excessive removal reduces shelf protection and increases dehydration in retail packs. Trimming prepares the bulb for consistent presentation and prevents tangles in bagging. Top trimming cuts the dried stem to a specified length. Cut length is controlled because too long catches in mesh packs and too short can expose the neck opening. Root trimming removes root remnants flush to the basal plate without cutting into the plate. Cutting into the basal plate can open pathways into cloves and reduce storage stability. Trimmers use rotating blades or abrasion heads with guides that center the bulb so the cut is consistent. After trimming, the bulbs pass through a second cleaning stage to remove fragments created by cutting. Gentle brushes smooth the wrapper and remove remaining loose flakes. Aspiration captures debris so it does not enter weighing systems. The cleaned bulbs then move into sizing and grading. Sizing is usually based on bulb diameter. Roller sizes, belt sizes, or optical systems classify bulbs into size bands. Roller sizes use parallel rollers with widening gaps. Smaller bulbs drop through earlier and larger bulbs ride further. Belt sizes use diverging belts that create increasing openings. Optical sizing uses cameras to measure diameter as bulbs rotate on rollers. The measurement system assigns each bulb to a lane that corresponds to a pack size class. Quality grading removes bulbs that would fail appearance or storage targets. Optical inspection systems evaluate surface color uniformity, wrapper integrity, and visible defects. They detect split bulbs, exposed cloves, mold, soft spots, and excessive scuffing. Split bulbs are a major defect because they dehydrate fast and do not hold shape in packs. Bulbs with missing wrapper layers are also flagged because cloves can show and lose moisture. Sorting uses air jets or gates to divert defects out of the main stream. A separate grading decision can be made for bulbs with attached stems when braided products are produced. In that case, the facility routes long stem garlic to braiding lines and short stem garlic to standard pack lines. Braiding requires stems that are dry yet flexible enough to be woven. Stem moisture and flexibility are therefore controlled during curing. Braiding lines separate bulbs by stem length and wrapper strength. After grading some lines, use a polishing step that improves appearance. Polishing uses softer brushes to smooth wrapper layers and reduce loose skin flakes. The purpose is not shine, but uniform wrapper texture. Polishing also reduces dust inside consumer packs. Packing formats for garlic are chosen to support ventilation and prevent condensation. The most common formats are mesh bags, net sleeves, and small cartons with ventilation holes. Garlic must breathe because residual moisture and respiration gases can accumulate in sealed packs and lead to mold. The packing line, therefore, uses materials with airflow paths. For mesh bags, garlic is portioned by weight. A scale accumulates bulbs until the target weight is reached. The portion drops into a bag, former that opens a mesh bag. The bag is sealed with a clip or heat seal depending on the material. Seal timing is set so no bulb sits in the seal zone. A label tag is applied. The filled bags are then conveyed to case packing. For net sleeves, the line forms a tubular net and loads a fixed count or weight. Clips seal the ends. Sleeve tension must be controlled because excessive tension can crush wrappers and create bruising at the basal plate. Size consistency is important in sleeves because larger bulbs increase tension and can distort the pack. For cartons or trays, bulbs are arranged in a single layer or in small stacks. Inserts can prevent rolling. Cartons are closed and taped or glued. Vent holes are lined to allow airflow through stacked cartons. Coding prints size class and lot identity. Check weighers verify carton weight within tolerance. For braided garlic, the process adds a weaving stage. Selected long stem bulbs are aligned and then woven into braids using guided fixtures. The braids are tied and trimmed. Braids are then packed in cartons with supports that prevent crushing. The braiding process relies on stems being dry enough not to mold, yet flexible enough not to snap. That balance is achieved during curing and by controlling humidity in the braiding room. Some facilities also produce peeled garlic and garlic cloves for food service. This route starts with grated bulbs that are sent to a breaking system. Breaking separates bulbs into individual cloves by mechanical cracking and rubbing. The cloves pass through an air separation system that removes papery skins. Additional peeling can use abrasion or air blast to lift remaining skins. Peeled cloves are washed briefly to remove skin fragments and then drained. Drain control is important because free water reduces shelf stability. The cloves are then sized and packed in sealed bags with controlled gas permeability, and then chilled quickly. Storage and staging are integrated into garlic packing because temperature and humidity control determine sprouting and mold risk. Packed garlic is held in cool, dry rooms. Temperature is kept low enough to slow sprout development. Humidity is kept low enough to prevent wrapper softening, but not so low that wrappers become overly brittle and flake. Airflow is managed, so conditions are uniform through pallets. Ventilation in cases and pallets allows air to move through stacks. Bell peppers become a consistent retail product inside a packing facility by being unloaded with low impact, washed and dried, sorted by size, color, and defect, then packed in protective formats that prevent scuffing and dehydration. The process begins at receiving where bulk bins or field totes are introduced to a line designed for delicate skins. Peppers are tipped by hydraulic dumpers onto cushion conveyors with very low drop height. The goal is to avoid compression bruises and skin tears that later become soft spots. In-feed belts spread peppers into a single layer so they do not rub against each other in piles. Side guides and belt speeds are tuned to prevent rollback and pinch points. A dry debris removal stage often comes first. Air knives blow off loose leaves and dust that would otherwise contaminate wash water. A scalping screen can remove stones and hard debris that could gouge skins downstream. Once gross debris is reduced, the peppers enter washing. Washing starts with a pre-rinse that removes surface soil and field dust. Spray bars deliver water at controlled pressure so the skin is cleaned without forcing water into the stem cavity. Water is filtered continuously because suspended grit can scratch the glossy surface. After pre-rinse peppers pass through brush washers where soft rotating brushes scrub the surface. Brush stiffness is chosen to avoid dulling the skin. Brush speed is set so peppers rotate and contact brushes evenly, rather than sliding. After brushing a clean rinse, stage flushes away loosened residues. Drain belts remove free water. Drying follows because wet peppers scuff easily and water droplets interfere with optical sorting. Air knives remove surface droplets, and a drying tunnel uses moving air to bring the surface to a consistent dry state. Air temperature is kept moderate so the fruit does not warm and soften. The drying goal is a dry skin with minimal water trapped near the stem. Sorting and grading begin once peppers are clean and dry. Singulation is the first step in grading because sensors require isolated items. Singulation belts separate peppers with controlled spacing. Rollers can rotate peppers so cameras see multiple views. Spacing is maintained so diverters can fire accurately. Optical inspection systems capture images under controlled lighting. Lighting is designed to reveal color uniformity and surface defects. Cameras measure size, shape, and color stage. They detect scuffs, cuts, sunken bruises, blossom end issues, and skin cracking. The system can also flag soft rot indicators when discoloration patterns match known defect signatures. Each pepper is assigned a grade and a destination lane. Color sorting is important because peppers can be green, red, yellow, or orange, and color uniformity is a retail requirement. Optical systems quantify hue and saturation. Mixed color peppers or uneven color peppers can be routed to processing grades. Uniform colored peppers are routed to premium packs. Sorting can also separate by gloss and by skin texture because dull peppers often indicate dehydration. Size grading is performed alongside quality grading. Size can be estimated from image geometry or measured by mechanical sizing cups. Many systems use weight grading as well because pepper density varies. Weight is recorded by in-motion scales that support the pepper briefly. Size and weight together support pack count targets and uniform appearance in trays. After the inspection zone, the line uses diverters to route peppers. Diverters are timed gates or air jets that move peppers into different lanes. Impact control at these diversion points is critical. Chutes are lined and curved. Drop heights are minimized. Accumulators buffer flow so peppers do not jam and compress. Each lane feeds a specific packing format. Some lines include stem trimming or calyx cleaning. Trimming is minimal because peppers are sold with stems, but excessive stem length can puncture adjacent peppers in packs. If trimming is used, it clips stems to a controlled length without damaging the calyx. Calyx damage increases moisture loss and rot risk. The trimmed peppers then pass through a brief air dry stage to remove any moisture at the cut side. Waxing is not always used for peppers, but a light surface treatment can be applied to reduce dehydration in longer distribution. If applied, it is done as a fine mist while peppers rotate. The coating is very thin because heavy films can trap moisture and dull the natural gloss. After application, peppers pass through a short drying tunnel to set the film. Packing is designed to protect skins from abrasion. The most common premium format is tray packing. Trays have cavities that hold each pepper and prevent rolling. Tray selection matches pepper size class. Trays are fed by a denister and placed on a conveyor. Peppers are placed into trays by synchronized drop lanes or robotic pick systems. Placement is oriented so stems do not face outward toward film surfaces or neighboring peppers. After trays are filled, they are overwrapped or lidded. Overwrap film is stretched over the tray and sealed. film tension is controlled, so it holds peppers without crushing them. Vent holes can be included to prevent condensation. Lid seal systems use heat-sealable films with controlled dwell time. Clean seals matter because leaks change humidity inside the pack and accelerate dehydration. For value packs, peppers can be packed in bags, often as mixed color packs. Bagging begins with portioning by count or by weight. Counting systems use gates and sensors to assemble a defined number. Weight systems use scales to hit target mass. The portion drops into a bag former. Bags are sealed and labeled. Bag material selection balances ventilation and moisture retention. Too much ventilation accelerates dehydration. Too little ventilation can trap moisture and promote soft spots. For bulk cartons, peppers are packed in layers with pads or liners. Liners reduce scuffing and help manage moisture. Carton fill is done with controlled drop heights and layer formation, so lower peppers are not crushed. Cartons are closed and taped or glued. Vent patterns in cartons support airflow in cold storage. Cooling and cold chain management are integrated into pepper packing. Peppers are sensitive to heat and soften quickly if held warm. Many facilities pre-cool peppers before packing or immediately after packing. Forced air cooling is common. Packed cartons are stacked with vent alignment, and fans pull cold air through the stack. Cooling rate is controlled to reduce water loss. Humidity in cooling rooms is maintained to prevent excessive dehydration while still avoiding condensation. Temperature targets are chosen to slow respiration and preserve firmness. Stable temperature prevents sweat formation on skins. Sweat leads to slip and scuff and later soft spots. The packing line therefore tries to keep peppers near a stable temperature from wash through pack, and it avoids warm air pockets around dryers by using moderate air temperatures. If the facility also produces cut peppers, the process branches after grading. Selected peppers enter a cutting room where they are washed again and then cored and sliced. Core removal cuts away the seed cluster and white ribs. Slicing blades are sharpened to avoid tearing skins. Slices are washed lightly to remove seeds and then dried by centrifuge or air. The slices are portioned and sealed in bags or trays and then chilled quickly. This route relies on very tight temperature control because cut peppers dehydrate fast. Quality checks occur throughout. Visual checks confirm color uniformity and defect rates. Weight checks confirm pack targets. Seal checks confirm package integrity. Rejected peppers are routed to processing grades or removed. The goal is to maintain grade purity and reduce damage introduced by the line itself. Watermelon slice candies are made by building a flavored sugar gel, shaping it into thick sheets or wedge forms, drying it to a defined chew, then finishing it with a sugar coat that gives the familiar grainy surface and prevents sticking. Production starts with the base syrup because every later step depends on solids level and water activity. Granulated sugar is screened to remove clumps and to keep crystal size consistent. Glucose syrup is stored in jacketed tanks so it can be pumped at a steady viscosity. Water is filtered and tempered because temperature affects how fast sugar dissolves and how stable the cook is. Acid powders and salt are staged in microfeeders because small shifts change sour balance and also change gel strength. Colors and flavors are staged as concentrates, so dosing stays precise when the line runs at high speed. A clear sugar solution is prepared first. Sugar and water enter a dissolver with strong agitation so crystals hydrate without settling. The dissolver runs until the solution is fully clear because undissolved grains can seed crystal growth later. Strainers remove any stray solids that could trigger graining or clog injectors. The clear solution then feeds a cooker where heat drives off water and raises solids to a target level. Cooking is controlled by temperature and residence time rather than by appearance. The goal is a repeatable solids concentration that will gel cleanly and dry predictably. If solids are too low, the candy dries slowly and stays sticky. If solids are too high, the gel sets too firm and can crack when cut. Glucose syrup is metered into the cook as a crystallization control tool. It reduces unwanted graining and keeps the final texture smooth rather than sandy. Once the syrup reaches target concentration, it is cooled to a blending temperature. Cooling is staged through heat exchangers, so the syrup remains fluid but no longer threatens sensitive ingredients. Acid is usually not added at peak heat because low pH at high temperature accelerates inversion and can change chew. Instead, acid is added after cooling as a solution for rapid dispersion. pH is checked because it influences flavor brightness and also affects how some gel systems are set. The gel system is prepared in parallel because it needs hydration time. Many watermelon slice candies use gelatin as the primary gelling agent, sometimes supported by starch or other hydrocolloids. Gelatin is bloomed in cold water, so granules swell evenly. It is then warmed gently until it becomes a clear solution. If starch is used, it is hydrated as a slurry and then cooked to develop viscosity. If other hydrocolloids are used, they are dispersed under high shear to prevent fisheyes and clumps. The cooled syrup and the gel stream meet in an inline mixer. The mixing goal is uniformity without air entrainment. Air bubbles create weak zones and cause cloudy spots in a translucent candy. Static mixers are often used because they create strong folding without whipping. The blended mass becomes a hot, viscous liquid that will set into an elastic gel as it cools. Flavor and color are added late. Watermelon flavor is usually a blend of volatile components that can be stripped by heat, so it is injected after the syrup has been cooled into the safe range. Oil-based flavor components are emulsified or carried so they disperse evenly. Color is added as 2 or 3 separate streams because the finished candy needs distinct layers. A typical slice has green at the rind, white as a thin buffer, and red or pink as the main body. Black or dark inclusions can be added to simulate seeds, but many styles keep a clean surface and rely on printing or speckling in the red layer. To create the layered look, the line either runs sequential casting into one mold or runs separate sheets that are laminated. In sequential casting, the green layer is deposited first into a flat tray or onto a belt. That layer is allowed to partially set so it can support the next deposit without mixing. A thin white layer is deposited next and partially set again. The red layer is deposited last and forms the bulk thickness. Timing is critical because if the first layer is too liquid, the colors bleed. If it is too firm, the layers do not bond and can delaminate later. In lamination-based production, each color is cast as its own thin sheet and cooled to a gel stage. The sheets are then brought together in a laminator that presses them into a single composite slab. Pressing must be firm enough to eliminate air at the interfaces. It must not be so firm that it squeezes layers unevenly. Lamination gives strong layer definition and allows each layer to be tuned for thickness more easily. Once the slab is formed, it is set and pre-dried. Setting brings the gel network to strength so it can be handled. Pre-drying begins moisture reduction so the slab can be cut cleanly later. In starch-molded systems, the candy sets in cavities formed in starch. But watermelon slices are often made as slabs because wedges cut more efficiently from a sheet. Slab setting is done in controlled air rooms where temperature and humidity are managed to avoid sweating. Drying is the step that creates the final chew. Fresh gel has more water than the finished candy. Drying moves the candy into a narrow moisture window where it is elastic and bite-resistant without being sticky. Airflow removes moisture from the surface, and then moisture diffuses outward from the interior. Drying must be slow enough to avoid case hardening. Case hardening creates a tough skin and a soft core. The line uses staged, humidity, and temperature, so the surface does not seal too early. As the slab dries, it becomes firmer and more cut stable. At this stage, seed effects can be introduced if the product uses them. Seeds can be small, dark sugar bits that are added during the red deposit. They can also be printed later, but printing is less common on sugar-sanded gummies because the surface is rough. When seed bits are used, they must be dry and stable, so they do not bleed color into the gel. After drying, the slab moves to cutting. Cutting begins with edge trimming because slab edges often have thickness variation from casting. Trims are collected for controlled rework depending on the recipe and moisture state. The slab then passes through a strip cutter that makes long bands at the width of a slice. A second cutter stamps or slices wedges from the bands. Wedge geometry is defined by the cutter profile and by the band width. Cutter speed is synchronized to belt motion, so piece weight stays consistent. Cut quality depends on slab temperature. If the slab is too warm, it smears and sticks to blades. If too cold, it can crack at the layer interfaces. Many lines use chilled, but not cold cutting conditions to get clean edges without fracture. Blade coatings and blade wiping systems reduce buildup. Some plants use ultrasonic blades because vibration reduces sticking on gummy textures and produces smoother cuts. Once wedges are cut, they often undergo a short conditioning stage. This allows cut faces to dry slightly so the pieces do not stick together. Conditioning also equalizes moisture after cutting because freshly exposed interiors release water more quickly. Controlled air prevents surface tack that would ruin the later sugar sanding. Sour balance is built in two places. Some of it is inside the gel through acid dosing. The sharp initial sour that many watermelon slices deliver often comes from the surface. Surface sour is applied by a sanding mix that combines fine sugar with acids, like citric and malic. The blend particle size is controlled so it clings evenly and dissolves at the intended speed. If particles are too fine, they cake. If too coarse, they fall off during conveying. To make sanding adhere, the candy surface needs controlled tack. The surface cannot be wet because the sugar will dissolve and form patches. It cannot be too dry because the sugar will not bond. Many lines use a very light mist of water or syrup to create temporary tack. The mist is extremely fine, so it wets only the outermost surface. Immediately after misting, the wedges enter a sanding drum, where the sugar acid blend is dosed and distributed by tumbling. Tumbling intensity is tuned to protect edges. Wedges have pointed tips and thin green rims that can chip. Drum speed and fill level are chosen to encourage rolling rather than sliding. Rolling spreads, sanding evenly across the faces and edges. After sanding, excess sugar is screened off and collected. A short drying tunnel follows. So, the tack layer sets and the sugar crystals lock onto the surface. Apples become a uniform retail product inside a packing facility by being stabilized, cleaned, sorted, graded, waxed, and packed under tight control of temperature, moisture, and impact. The process starts when bulk field bins of apples enter a receiving line that is designed to keep bruising low. The bins are tipped by a hydraulic dumper into a water flume or a dry cushion infeed. A flume is often used because water supports the fruit and reduces drop impact. Flow rate is set so apples separate and do not pile up. If a dry infeed is used, soft belts and low drop chutes spread the fruit into a single moving layer. From the infeed, the apples pass through a pre-rinse stage that removes loose dust and leaf fragments. Spray bars deliver water at controlled pressure, so surface debris lifts without forcing water into the stem cavity. The rinse water is filtered continuously because suspended grit can scratch skins. The fruit then moves into a washer where rotating brushes scrub the surface. Brush stiffness is chosen by variety because thin-skinned apples mark more easily. Brush speed is tuned so the fruit rotates and contacts brushes evenly instead of sliding. After brushing, the apples pass under high-volume rinses that flush away loosened residues. Drain belts and air knives remove excess surface water. Drying matters because downstream optical cameras need a stable surface reflectance. Drying also matters because wax application behaves differently on wet skins. The line often uses warm air tunnels to bring the surface to a consistent dryness without heating the fruit core. Before deep sorting, the line removes obvious non-conforming fruit mechanically. A sizing roll section can separate very small fruit that will be routed to other packs. A singulation belt then spreads apples into a consistent spacing. Singulation is one of the most important steps because all later measurement systems assume each apple is isolated. Belt speeds and lane dividers maintain spacing as fruit enters the inspection zone. Optical inspection is the central grading step. Multi-angle cameras capture images of each apple as it rotates on rollers. Lighting is controlled to reveal color, gloss, and surface defects. Algorithms measure diameter, shape, blush coverage, and background color. They also detect bruises, punctures, russeting, scab, hail marks, and stem cavity damage. Some lines add near-infrared sensing to estimate internal defects or maturity indicators. The result is a decision for every apple that determines its pack grade and its destination lane. At the same time that cameras inspect surface quality, the system measures size and weight. Size is derived from image geometry and from mechanical calipers in some designs. Weight is measured by in-motion scales that momentarily support the apple and record load. Size and weight are combined because many pack specs are defined as count per carton. Count targets require tight weight distribution, so the packed box stays within tolerance while keeping visual uniformity. Once each apple has a grade and size assignment, the line uses diverters to route it to the correct channel. Diverters can be air jets or flap gates or servo paddles. Timing accuracy is critical because fruit is moving continuously. Each apple's position is tracked from the cameras to the diverter, so the correct gate fires at the correct moment. Mistiming causes cross-grade contamination and forces rework. Many packing lines apply wax after washing and before final packing. Wax is not just cosmetic. It reduces moisture loss and stabilizes gloss. Wax is applied as a fine mist or a roll coat while apples rotate. The wax formula is chosen to form a thin continuous film without streaking. Application rate is controlled because heavy wax can look cloudy and can trap dust. After wax application, the fruit passes through a drying tunnel. Warm airflow sets the film and fixes shine. If stickers are applied, they are placed after waxing and after the surface is dry. A label head peels the sticker and presses it onto the fruit with controlled force. Placement is consistent, so labels do not wrinkle over lenticels or curve edges. The label system is synchronized to fruit spacing, so every selected apple receives one label and the label stays aligned. At this point, the line can split into two main product routes. One route is whole fruit packing. The other route is further processing into fresh cut slices or value packs. For whole fruit packing, the apples enter a packing accumulator that buffers flow. From there, they feed into either tray packing or loose fill systems. Tray packing uses molded fiber or plastic trays that hold each apple in a pocket. Tray selection is based on size count. A tray denester places an empty tray on a conveyor. Apples are then placed into pockets by synchronized drop lanes or robotic pick heads. Pocket depth and spacing. Reduce movement in the carton and protect skins from rubbing. Loose fill packing is used for bags or bulk cartons. In this route, apples drop into a bag former or into a carton with controlled drop height. Shoots are lined and curved to minimize impact. For bagging, a weighing system portions a target mass. Apples are released into a plastic bag and the bag is sealed. Bag seal timing is coordinated with the drop, so no fruit is caught in the seal. For bulk cartons, the system fills in layers to avoid tall drops. A leveling gate can settle apples into a stable arrangement. Carton formation is integrated into the packing line. Flat blanks are erected into cartons by a case erector. Trays or loose apples are loaded into the carton. A top pad can be placed to reduce scuffing. The carton is then closed and taped or glued. Coating prints a lot identifier and pack information. Check weighers can verify carton weight against expected range. Vision checks can confirm proper closure. A critical part of apple production is storage management inside controlled conditions. Many apples are held in cold storage before packing. Cold storage slows respiration and maintains firmness. Temperature is held near a set point and humidity is controlled to limit dehydration. Many systems use controlled atmosphere storage where oxygen is reduced and carbon dioxide is managed. This slows metabolic activity and preserves texture. Before packing, fruit is often tempered to a target temperature, so condensation does not form on skins when the fruit hits warmer air. Tempering also stabilizes wax behavior and camera performance. When the product route is fresh cut apples, the process changes after washing and sorting. Only fruit that meets internal quality targets is selected because cutting amplifies defects. Selected apples enter a coring and slicing system. The apple is centered by a cup and then pushed onto a corer. The corer removes the core and seeds in one stroke. Slicing blades then cut the apple into wedges or rings. Blade sharpness is tightly maintained because dull blades crush tissue and accelerate browning. The slicing system is designed to keep cut surfaces clean and consistent thickness. Fresh cut apples require anti-browning control. Immediately after slicing the pieces, enter a dip or spray treatment that slows enzymatic browning. The treatment is metered and contact time is controlled. Excess solution is removed by drainage and gentle air. The slices are then portioned into packs. Portioning can be done by weight or by piece count. Packs are sealed with films that control moisture and gas exchange. Some packs use modified atmosphere to slow oxidation. Sealed packs are chilled quickly to stabilize texture. Whether whole or sliced, the final steps focus on protecting quality through handling. Conveyors are designed with soft transfers. Drop heights are minimized. Accumulation tables prevent jams that would compress fruit. Packaging materials are chosen to resist moisture transfer and to maintain structure in cold environments. Cases are palletized in stable patterns that allow airflow during cold chain storage. Mangoes become a consistent retail product inside a packing facility by being stabilized, cleaned, heat treated when required, graded by size and maturity, cooled, waxed, and packed under tight control of temperature and impact. The process begins with bulk field bins or crates entering a receiving line designed to limit bruising. Mangoes are tipped by a hydraulic dumper into a water flume or onto cushioned belts. A flume supports the fruit and reduces drop energy. Water flow is adjusted so mangoes separate and do not stack. If a dry dump is used, the system relies on soft curtains and stepped chutes to spread fruit into a single moving layer. From in feed, the fruit passes through a pre-rinse stage that removes dust and sap residues loosened during harvest and transport. Spray bars deliver water at controlled pressure so the skin is cleaned without forcing water into lenticels. The rinse stream is filtered continuously because grit in recirculated water can scratch skins. Mangoes then enter a washer where rotating brushes scrub the surface. Brush stiffness is selected by variety because skin sensitivity varies. Roller speed is tuned so each fruit rotates and contacts brushes evenly. A key mango-specific step is sap management. Mango latex can mark skins and cause dark streaks. The wash sequence is configured to remove sap films early. Water temperature and contact time are controlled to lift residues without softening the skin. After brushing, high-volume rinses flush away loosened residues. Drain belts and air knives remove surface water, so downstream, sensors see a consistent surface reflectance. Many mango lines include a hot water treatment step when required by export specifications or when a heat treatment is used to stabilize quality. The treatment uses a temperature-controlled water bath with precise residence time. Mangoes enter baskets or carriers that submerge them uniformly. Water temperature is monitored continuously because small deviations change treatment effectiveness and can also stress the fruit. Residence time is controlled by conveyor speed or basket dwell. After treatment, mangoes exit and move immediately to cooling. Cooling is staged to remove heat without creating surface condensation. A first cooling step can use a water rinse at controlled temperature. A second step uses forced air cooling tunnels to bring fruit to a target core temperature. Airflow is designed to reach all sides without creating localized cold spots. Temperature equalization matters because uneven cooling can create localized ripening differences. After washing and any treatment, the fruit enters singulation. Singulation spreads mangoes so each piece can be inspected and measured individually. Lane dividers and timing belts create consistent spacing. Proper spacing is required for accurate imaging and for correct diverter timing. Mangoes then move into an inspection zone where lighting and camera angles are controlled. Optical grading is used to classify mangoes by size, color, shape, and surface defects. Cameras capture multiple views as mangoes roll over rollers. Lighting is configured to reveal bruises, scuffs, sap burn marks, blemishes, and sunspots. Algorithms measure size and estimate volume. Some systems use near-infrared sensing to estimate internal maturity indicators such as dry matter or internal defects. The purpose is to route fruit into ripeness programs and pack grades. Weight grading can be added with in-motion scales. Each mango passes over a support that records weight. Weight data is combined with size data to assign a count class for cartons. Consistent count class is important because cartons are sold by count and expected to look uniform. The system routes mangoes into lanes that correspond to target count and grade. Maturity management is a central control point for mango packing. Mangoes continue ripening after harvest. The facility often receives fruit at different maturity levels. Sorting can separate greener fruit for longer distribution from more colored fruit for near-term delivery. When maturity sensors are used, the system can build lots with consistent dry matter and color stage. This reduces mixed ripeness in a single carton. Once each mango is assigned a destination lane, diverters route the fruit. Diverters can be servo gates or drop belts that release fruit into the correct lane. Timing is precise because mangoes are moving continuously. Impact control at diversion points is critical because mangoes bruise easily. Chutes are lined and curved. Drops are kept low. Accumulators are used to prevent pileups. After grading many lines, apply a wax or coating. The coating reduces moisture loss and improves appearance. Wax is applied as a fine mist while fruit rotates. Application rate is controlled because heavy wax can create streaks and trap dust. After waxing, mangoes pass through drying tunnels where warm air sets the film. Drying air is controlled so it sets wax without warming the fruit excessively. If stickers are required, they are applied after wax and after the surface is dry. A labeling head places a sticker at a consistent position. Placement force is controlled so the sticker adheres without tearing the skin. Label application is synchronized with fruit spacing, so no fruit is missed and no double labels occur. Packing begins with staging fruit into packing buffers. Buffers equalize flow and allow packers to fill cartons at steady speed. Mango packing often uses trays or single-layer cartons to reduce bruising. Tray packing uses molded inserts with pockets. Pocket size is matched to mango size class. Fruit is placed into pockets by synchronized lanes or by pick systems. Pocket orientation is controlled, so stem ends are positioned consistently when required by presentation standards. For loose fill or bulk cartons, the line uses gentle filling chutes. Mangoes are layered rather than dropped in a deep pile. Layering reduces pressure on lower fruit. Pads or liners can be placed between layers. The objective is to prevent pressure points that become bruises. For bag formats, mangoes are weighed into target weights and dropped into bags with controlled drop height. Bags are sealed and then packed into cases. Carton erection and closing are integrated into the line. Flat blanks are erected into cartons by a case erector. Trays or loose fruit are loaded. The carton is closed and taped or glued. Codes are printed to identify lot and pack date. Check weighers confirm cartons are within tolerance. Vision systems can confirm closure integrity. Cold chain control continues after packing. Mangoes are moved into cold rooms set to a target temperature that slows ripening without causing chilling injury. Temperature set points depend on variety and maturity stage. Airflow in. Storage is designed to cool cartons evenly. Humidity is controlled to reduce dehydration while preventing condensation. Carton vents align to allow airflow through the stack. Some supply chains use controlled atmosphere storage or transport. Oxygen and carbon dioxide levels can be adjusted to slow metabolism. Gas control must be stable because excessive carbon dioxide can cause off flavor and internal injury. Even without controlled atmosphere, the core control is maintaining stable temperature through storage and transport. If the facility also produces fresh cut mango, the process branches after grading. Only fruit meeting internal quality targets is selected. Mangoes are peeled using mechanical peelers or knife systems that remove skin with minimal flesh loss. Flesh is sliced from the seed with guided blades. The slices are cut into cubes or strips with calibrated cutters. Cut size is controlled because it affects drainage and pack appearance. Cut pieces are chilled quickly to slow softening. They are portioned into packs by weight and sealed. Packaging films are selected to manage moisture and oxygen exchange. Reese's peanut butter cups are manufactured by building two materials that behave in opposite ways and then forcing them to meet cleanly at high speed. The chocolate must flow like a liquid in the depositor, then crystallize into a rigid shell that releases from tooling. The peanut center must be soft enough to bite with a short crumble, yet stiff enough to hold shape, resist oil separation, and accept a top seal without squeezing out. The peanut component begins with roasted peanuts that are converted into a paste with tightly controlled temperature. Incoming kernels are cleaned and screened, so shell fragments and fines are removed before grinding. Roasting level is chosen to drive down moisture and develop aroma while keeping oils stable. After roasting, the nuts are cooled quickly so residual heat does not thin the paste and accelerate oil separation during storage. Grinding is staged because peanut butter texture depends on particle size distribution and shear history. A coarse grinder breaks kernels and releases oil, creating a continuous fat phase. A second grinder refines particles to the desired smoothness. Friction heats the paste, so grinders are jacketed or throughput is controlled to keep temperature in a narrow range. If the paste warms too much, it becomes overly fluid and later produces a filling that flows and smears. If too cool, it becomes stiff and resists blending with dry powders. The paste then moves into filling formulation. The goal here is not a spreadable peanut butter, but a depositable confection that sets with a slightly crumbly bite. Fine powdered sugar is the main structure builder. It is sifted so clumps are removed because clumps create dry pockets and inconsistent dosing. Salt and flavor components are prepared as micro additions. A compatible fat stream may be used to tune firmness and melt profile, and emulsifiers are staged to stabilize the oil phase and improve flow through depositors. Mixing is done in high torque equipment because the peanut paste thickens dramatically as powders are added. The paste enters first, then powders are introduced in a controlled feed, so the mix wets gradually rather than forming dry rafts. As sugar absorbs free oil, the mass becomes less glossy and more plastic. Mixing energy is tuned to avoid turning the mass into a smooth, homogeneous paste. Too much shear breaks the short structure and yields a slick filling that feels less crumbly. Too little shear leaves dry streaks and causes weak spots that crack under the chocolate cap. Temperature control during filling mixing is a core lever. The mass must be warm enough that it can be pumped and metered, but not so warm that it relaxes and spreads inside the cup. Jacketed mixers and conditioned hoppers hold the filling in a narrow temperature band. The filling is often moved through a short conditioning step after mixing so fat crystals can begin forming and the texture becomes more consistent. This conditioning also allows entrained air to rise out. Large bubbles create voids that later collapse and cause dents in the top surface. While the filling is being prepared, the chocolate system is built for shell formation. Chocolate is melted, filtered, and held at a stable temperature, so viscosity is constant. The key operation is tempering, which establishes a controlled population of stable cocoa butter crystals. Tempered chocolate behaves like a fluid at the depositor, but solidifies quickly into a glossy, firm structure. Tempering is maintained by staged cooling and reheating within a continuous unit, with sensors watching temperature and flow resistance as indirect signals of crystal content. The forming line starts with paper liners. Liners are denested and placed into cavities on a moving mold plate. Cavity fit is controlled because the liner must be supported to prevent wrinkling when chocolate is spun. Liner placement accuracy matters because a shifted liner creates thin shell walls on one side and thick walls on the other, which leads to breakage during demolding and uneven bite. Shell formation is done by depositing a metered shot of tempered chocolate into each lined cavity and then immediately shaping it into a cup. The shaping step is usually a spin or a combination of spin and vibration. Spinning forces chocolate up the liner walls and leaves a hollow center. Spin time and speed define wall thickness and rim height. If the spin is too aggressive, walls become too thin and crack later. If too gentle, the shell becomes heavy and reduces space for filling. Vibration during or after spinning helps remove bubbles and smooth the interior surface. The newly formed shells enter a brief cooling zone. This is not full hardening. It is a partial set that makes the shell self-supporting but still receptive to bonding with the filling. Cooling must be controlled because an overly cold shell can create poor adhesion and delamination. An overly warm shell can deform when filling is deposited and can create uneven rim geometry. Filling deposition is engineered to place a consistent puck inside the shell without contaminating the rim. The filling is delivered from conditioned hoppers to deposit heads that meter precise volumes. Depositing can be a single shot that forms a dome or a spiral that levels more evenly. The deposit height is controlled so there is clearance for the chocolate top. If filling touches the rim, it interferes with sealing and creates weak edges. Many lines use a light vibration or a short dwell to let the filling settle into a consistent profile, but the motion must be gentle because too much vibration can smear filling into the shell wall and create uneven thickness. Top sealing is created by depositing a second shot of tempered chocolate. The chocolate must flow outward enough to meet the shell rim and form a continuous bond. Deposit volume sets top thickness. Too thin a top can crack during handling. Too thick a top dominates bite and slows cooling. Some lines apply a short vibration after topping to level the surface and release trapped air. This vibration is tuned to avoid chocolate climbing the liner edge and creating flash. Once topped, the cups enter the main cooling tunnel. Cooling is staged because chocolate crystallization must be guided into a stable form. The first zone sets the surface quickly to prevent smearing and to lock the top shape. Subsequent zones cool more gradually so the entire chocolate mass crystallizes uniformly without internal stress. Exit temperature is chosen so the cups are rigid enough to demold and convey without scuffing. During cooling, the filling also stabilizes. Fat crystals within the peanut mixture continue forming and the filling becomes firmer and more brittle in its short structure. This is essential for the characteristic bite. If the filling remains too soft, it will squeeze under pressure and cause top separation. If it becomes too hard, it loses the expected crumble and becomes a dense block. Demolding releases the lined cups from the mold plate. Release depends on correct temper and correct cooling because the chocolate must contract slightly away from the cavity walls. Gentle ejectors or inversion steps drop the cups onto belts. Handling is kept low impact because rims can chip and liners can crease. Once on the belt, cups can pass through inspection stations. Vision checks can detect missing tops, off-center fills, and liner misplacement. Weight checks confirm dosing accuracy and flag missing deposits. Packaging is designed around preventing temperature rise and abrasion. Individual cups are often flow-wrapped. Wrapping film is formed around each cup and sealed with controlled heat and dwell time. Heat must be sufficient to seal film without warming the chocolate surface enough to mark. Film tension is controlled so it does not crush the cup. For multi-pack formats, cups are collated into trays or sleeves that prevent movement and protect rims. Cartoning then adds stiffness and stack strength. Case packing arranges cartons to reduce compression and minimize vibration that could crack chocolate edges. Skittles are manufactured by making a chewy center that behaves like a resilient pellet, then growing a hard sugar shell around that pellet in hundreds of small additions, then adding color and a final finish so every piece looks identical and moves cleanly through packaging. The center is engineered first as a thermoplastic candy rather than as a syrup. Sugar and glucose syrup are treated as structural ingredients that control glass transition and chew. Granulated sugar is screened so crystal size stays consistent and dissolution is predictable. Glucose syrup is held warm in jacketed tanks so it meters smoothly and does not pulse. Water is filtered and tempered because small temperature changes affect the cook profile. Acids and salts are staged as micro additions because they influence both flavor and how the cooked mass behaves during conditioning. A dissolving step makes a clear feed syrup. Sugar and water are mixed under heat with strong agitation until no grain remains. Any undissolved grain would later seed crystallization and create weak spots in the center. The clear syrup then enters a continuous cooker or batch cooker where it is concentrated to a high solids level. Heat input is rapid to minimize time at elevated temperature because long heat exposure darkens sugars and shifts texture. In many lines, the syrup is heated under pressure and then finished with a flash step that removes water quickly and tightens final moisture. Cook endpoint is chosen to produce a mass that can be shaped without sticking and without cracking. If moisture is too high, pellets deform and flatten during later tumbling. If moisture is too low, pellets become brittle and can fracture under coating impacts. The cooked base is therefore delivered to a cooling stage that drops temperature to a range suitable for adding sensitive components. Flavor for the center is not the same as the final flavor experience because much of Skittles' character is carried by shell and aroma at the surface. Even so, the center is commonly given a base flavor note and a consistent sweetness profile. Flavors are injected after the hottest zone to preserve volatiles. Acids may be split between center and shell strategy. A portion of acid can be added late to set a baseline tartness without weakening the center structure. Mixing downstream uses static mixers or low shear manifolds to avoid entraining air. The cooked mass then becomes a plastic dough and enters forming. Forming begins by pushing the mass through an extrusion head that produces ropes at a fixed diameter, or by delivering it directly to a pellet former, depending on equipment design. Rope diameter is is a major variable because shell thickness is added on top, so the core size must stay tight to hit final piece size. A synchronized knife cuts the rope into pellets. Cut timing is locked to belt speed, so pellet mass stays consistent across the run. Fresh pellets have cut faces and a warm surface. They are transferred immediately to a rounding stage where they tumble and roll. Rolling knocks off sharp edges and produces the characteristic rounded shape that will coat evenly. This stage also seals micro cracks at the surface by gentle friction warming. Rounding is tuned to avoid smearing because smearing creates flats that later show as uneven shell thickness. After rounding, the cores go through conditioning. Conditioning is a controlled cooling and rest that stabilizes temperature and moisture through each core. The cores must be firm enough to withstand repeated coating cycles, but the surface must still accept initial shell adhesion. Conditioning airflow and temperature are set so surfaces are dry to the touch, while the interior retains the desired chew. Shell building is performed in rotating coating pans or perforated drums. The drum creates a rolling bed of cores that continuously cascades. Cascade behavior is controlled by fill level and rotation speed. A stable cascade ensures every core sees the same exposure to syrup spray and drying air. If the bed slides rather than rolls, pieces develop flat faces and shell becomes uneven. The first shell layers are engineered as a bonding bridge. A relatively light syrup is sprayed in short pulses. Droplet size is kept fine, so the film spreads thinly and evenly. Dry air immediately follows to evaporate water and begin crystallization. These early coats must set quickly to prevent pieces sticking together, and they must not add enough water to soften the core surface. Once the first layers lock on, bulk shell growth begins. A higher solid syrup is sprayed, and fine sugar is often dusted onto the wet surface. The dust absorbs moisture and accelerates set while increasing build rate. Airflow then dries the layer and forces crystallization. This spray, dust, and dry cycle is repeated many times. Each cycle adds a tiny increment of thickness, so stress remains low and cracks do not form. Drying is the most sensitive control in shell growth because it governs how crystals form within each layer. If drying is too fast, the surface can harden while moisture remains inside the layer, creating a trapped core that later pits or fractures. If drying is too slow, the surface stays tacky and pieces can twin. Twin formation is prevented by matching spray volume to drying capacity and maintaining continuous rolling so wet surfaces do not remain in contact. As thickness increases, the process shifts to smoothing. Powder addition is reduced, and the system relies more on thin syrup films that flow into micro valleys. Longer dry times then lock a smoother surface. Smoothness matters because it improves shine and prevents scuffing, and it provides a better substrate for printing. Color is applied as a sequence of thin coats rather than a single heavy dye layer. Color solutions are prepared to precise concentration and filtered so no particulates enter spray nozzles. Color is introduced when shell thickness is near target, so pigment remains close to the surface and looks bright. The drum receives a light color spray, then drying air sets it fully. Multiple passes build saturation evenly. Heavy color application would pool and create blotches, especially where shell microtexture is still present. Because Skittles are produced in multiple colors, runs are typically separated by color. Each color run uses its own color dosing and its own endpoint checks. Between colors, spray circuits are flushed to prevent cross tint. Shade is monitored by optical measurement on samples, and adjustments are made by changing pass count or concentration rather than by altering the underlying shell build. After color, clear finishing coats can be applied to improve durability and reduce rub-off. These coats are very light and followed by longer drying to reach a stable moisture endpoint. Moisture endpoint is critical because a slightly damp shell scuffs and sticks, while an overly dry shell can become brittle and chip under impact. The letter marking is applied near the end of finishing. Printing uses edible ink, transferred by a pad or similar contact method. Pieces are fed into a system that presents a stable face and applies the mark. Surface condition at this moment matters. The shell must be smooth and dry so the ink bonds and does not smear. A short drying stage follows, so the mark sets before pieces rub against each other. Polishing is the final surface operation. A very small amount of polishing agent is misted onto the tumbling pieces. the film spreads through contact and fills micropores, increasing gloss and reducing friction. Reduced friction helps pieces flow through packaging machines and reduces scuffing in bags. Polishing is controlled carefully because excess film can feel waxy and can interfere with print clarity. After polishing, the pieces are conditioned briefly to equalize moisture and temperature. Equalization reduces internal stress in the shell and improves resistance to fine cracking. Screening then removes fines, broken pieces, and twins that escaped earlier control. Size classification can be used to remove out-of-band pieces that would stand out in packs and behave differently in weighers. Packaging begins with gentle conveying into multi-head weighers. The pieces must flow freely without bridging. Hopper design and surface finish reduce sticking. The weigher selects combinations of small hopper dumps to hit target weight quickly. The portion drops into a form-fill seal machine, where film is formed into a tube and sealed above and below the product drop. Seal timing is set, so candies do not lodge in the seal zone. Clean seals are essential because moisture ingress softens shells and dulls gloss. For tube or carton formats, dosing can be by count or by volume, but the same requirement applies. Piece size distribution must be tight so count accuracy stays high, and so packs feel consistent. After filling, closures are applied and coating is printed. Packs are checked for weight and seal integrity, then case packed. Milka chocolate is manufactured by turning cocoa and dairy ingredients into a low moisture, fat continuous suspension with a very narrow particle size range, then setting that suspension into bars through precise crystal control and staged cooling. The line begins by stabilizing dairy inputs because milk solids introduce both flavor and a strong sensitivity to water. Milk arrives as powder, concentrate, or a pre-processed dairy ingredient depending on the plant setup. Powdered streams are sieved to break agglomerates because compacted milk lumps do not disperse evenly and later show up as grainy flecks. If liquid dairy or concentrate is used, it is filtered and held at controlled temperature, so viscosity and dosing remain stable. Sugar is handled as a dry engineered solid, screened for consistent crystal size, because crystal size determines refining load and final mouthfeel. Cocoa components enter as cocoa liquor, cocoa butter, and sometimes cocoa powder. Cocoa liquor is kept warm so it stays pumpable, while cocoa butter is melted and filtered so it meters cleanly. A key upstream objective is removing free water from the system early because water drives chocolate thickening and unstable flow. When the process uses a crumb route, milk and sugar are combined and cooked into a dry matrix before they ever meet the final chocolate fats. The milk-sugar mixture is heated under controlled mixing, so sugar dissolves and water evaporates. As water leaves, the mix transitions from syrupy to granular, and then to a dry crumb. Endpoint is set by moisture content and by how the crumb fractures. Too wet yields a crumb that later makes chocolate seize and thicken. Too dry yields excessive browning and harsh cooked notes. Once the crumb reaches endpoint, it is cooled and milled to a manageable particle size, so it blends uniformly downstream. If the process does not use a crumb route, the same moisture goal is achieved by strict control of powder moisture and by downstream conching, but the plant still treats water as the enemy of stable rheology. All ingredient handling and air exposure is therefore designed to keep humidity pickup low. Mixing creates the first chocolate mass. Cocoa liquor and a portion of melted cocoa butter enter a mixer to form a fluid fat phase. Crumb or milk solids and sugar are then introduced gradually, so particles become wetted rather than floating as dry islands. The mixer uses high torque and wall scraping because the mass is thick at this stage. The target is a uniform paste where solids distribution is even and there are no dry pockets. This paste is not yet smooth, but uniformity here prevents downstream refining streaks. Refining is where smoothness is physically created. The paste is fed to roll refiners or an equivalent milling system that reduces particle size into the low tens of microns. Roll refining squeezes the mass through a series of narrowing gaps, breaking sugar crystals and milk solids into smaller particles. The output leaves the final roll as thin flakes. These flakes have very high surface area and very little free fat at their surfaces, so they behave dry and dusty unless they move quickly into the next stage. Conching transforms refined flakes into a stable flowing chocolate by completing fat wetting and removing trace moisture. In a conch, paddles or rotors knead the chocolate under controlled heat. Mechanical work breaks down remaining agglomerates and forces cocoa butter to coat every particle. Heat keeps fats fluid, while airflow carries away moisture and volatile compounds. Moisture removal is not optional because even a small amount of water pushes viscosity up sharply. Conching is therefore run as a controlled balance between temperature, shear, and venting, so the mass becomes fluid without overheating. During early conching, the mass can appear crumbly and resistant because particle surfaces are not fully wetted. As conching continues, friction drops and the mass becomes glossy and pumpable. Viscosity and yield stress are the process indicators because they determine whether the chocolate will deposit cleanly into molds and whether it will release cleanly after cooling. Emulsifiers are introduced late in conching to fine-tune flow. Lecithin reduces yield stress by improving particle wetting. Additional flow modifiers can be dosed to reduce viscosity further at the same fat content. Dosing is precise because tiny changes alter curtain behavior, depositor accuracy, and final snap. Once conched, the chocolate is held in tempered storage tanks at a stable temperature with gentle agitation. Filtration removes any unmelted lumps or foreign particles before tempering. At this point, the chocolate is chemically and physically ready, but its fat crystals are not yet in the correct form for molding. Tempering is the controlled crystallization step that makes the final bar glossy, hard, and stable. Cocoa butter can solidify into multiple crystal forms, but only specific forms produce the desired contraction and snap. Tempering machines first heat the chocolate enough to melt all existing crystals. They then cool it under agitation so crystals nucleate. The chocolate is then reheated slightly to melt unstable crystals while leaving stable seed crystals. The output is a chocolate that remains fluid at the working temperature but contains a measured population of stable seeds. This seeded chocolate feeds molding. Molds are cleaned and temperature conditioned so the surface is dry and does not shock the chocolate. Deposit heads meter chocolate into each cavity with tight mass control. Immediately after deposit, molds pass over vibrating tables. Vibration releases trapped air bubbles and levels the surface so the bar face is smooth. Vibration also helps chocolate flow into fine embossed details if the mold carries a design. Cooling tunnels then set the chocolate. Cooling is staged because the goal is to crystallize the entire bar without creating stress. The first zone sets the surface quickly so it holds shape. Subsequent zones cool more gradually so stable crystals grow through the thickness. If cooling is too fast, internal stress can lead to cracks or later bloom. If cooling is too slow, throughput drops and the chocolate may stay soft long enough to pick up marks. Air humidity is controlled in the tunnel to prevent condensation because moisture on the surface can cause sugar bloom and dullness. As the bar cools, it contracts slightly. This contraction is essential for demolding. Correct temper and correct cooling create a bar that releases cleanly when the mold is inverted or flexed. After release, bars move onto conveyors that minimize scuffing. Any surface abrasion at this stage will remain visible after wrapping. Inspection can be integrated immediately after demolding. Vision checks can detect surface voids and broken corners. Weight checks confirm deposit accuracy. Bars outside tolerance are diverted. Reworked chocolate is collected and remelted, then returned upstream in controlled proportions so it does not destabilize tempering. Wrapping protects the finished bars from moisture, oxygen, and physical marks. Bars are indexed into wrapping machines that fold film or foil around them. Fold geometry is controlled so the wrap sits tight without crushing edges. Heat sealing parameters are tuned to close the film without warming the bar enough to soften the surface. Coating is applied for traceability and packs are checked for seal integrity. Cartoning and case packing follow for multi-unit formats. Cartons provide stacking strength and protect wrapped bars from puncture and abrasion. Cases are built and sealed for transport. Storage temperature stability is maintained to protect the cocoa butter crystal network because temperature swings can encourage bloom and soften snap.